Hi, it's time for another math easy solution. Today I'm going to go over further into infinite sequences and series and go over another epic long video. And this time it's on absolute convergence and the ratio and root test. So let's just jump right in. And like always, if you don't have time to watch this whole video, you can watch this at faster speed. There's some links and my recommendations, as well as I made a video on faster speed. It's pretty amazing. And also you can download and read the notes or view the notes on Steam. It's on Steam in article format. Links in the description below. And also you can watch the video in parts. Unless you're watching at fast speed, then you could watch it in one go if you're brave enough. Anyways, let's just jump right in. So let's look at, first thing, as always, I want to make a note, the calculus book reference that, note that I mainly follow along the following calculus book, and in this video is no different. So this is the Calculus Early Transcendental 6th edition by James Stewart. And let's look at the topics to cover. Topic 1 or part 1 is absolute convergence. Look at definition 1, then go over example 1, example 2, and then conditional convergence. Look at definition 2, theorem 1, example 3, and then look at the ratio test, and then look at example 4, go over a note on estimating sums, example 5, note on the ratio test, then go over the root test, go over example 6, then discuss rearrangements of series, and then look at exercises, some 4 of them that are pretty epic. Yeah, they're pretty epic, and if you see my earlier videos, the exercises usually take a big bulk of the video, just because you learn a lot more going through the exercises, oftentimes, than just the notes. So exercise 1, then exercise 2 is proof of the root test, which I go over in topic 4. Then go over exercise 3 and exercise 4. So let's jump right in. So absolute convergence. Given any series, the summation of an, we can consider the corresponding series where we take the absolute values of each term. So if we have the summation n equals 1 up to infinity of absolute value of an, like this, then we'll have, these terms are going to be the absolute value of a1 plus absolute value of a2 plus absolute value of a3 plus dot 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 and so on. And this series whose terms are the absolute value of the terms of the original series. So yes, we just take absolute value of each term. And now this brings me up to definition 1. So a series, the summation of an is called absolutely convergent if the series of absolute values, the summation of the absolute value of an is convergent. So it's absolutely convergent. If it's convergent for the absolute values, then it's absolutely convergent. Very interesting framing or label there. All right, let's go further. So notice that if the summation an is a series with positive terms, then the absolute value of an is just equal to an. And so absolute convergence is the same as convergence in this case, they're all positive. Also note that in my earlier videos, I went over convergence tests for series with positive terms and for alternating series. But what if the signs of the terms switch back and forth irregularly as opposed to these alternating back and forth directly? We will see in example 3 later in this video that the idea of absolute convergence sometimes helps in such cases. Alright, so now this brings me to example 1. So over here, this states this series, and you have summation from n equals 1 to infinity of this negative 1 to the power of n minus 1 divided by n squared. In other words, we have an alternating series here. When you plug in 1 here, you have a power of 1 minus 1 is 0, and 0 is going to be positive 1. Then when it's 2, you'll have an odd number, and that's going to be a negative. And then when you have it equal to 3, the third term, we're going to have 3 minus 1 is even, so it's going to be positive, then negative, and so on. So you're going to have something that looks like this. 1 equals 1 minus 2 squared plus 1 over 3 squared minus 1 over 4 squared plus dot dot dot. So this series is absolutely convergent because, well, what we could do is if we take the absolute value of each term, so let's just take the absolute value, the summation from n equals 1 up to infinity of the absolute value of, like this, n minus 1, negative 1 to the power of n minus 1 divided by n squared. This equals to Yeah, this equals 2, so this n squared is always positive. The only thing that's going to change is this negative 1. It's always going to be positive, so that just equals to 1. So this is going to be, well, everything's just going to be positive. It's going to be 1 plus 1 over 2 squared. And then this is going to be plus 1 over 3 squared plus 1 over 4 squared plus dot, dot, dot. And yes, recall that this is convergent because it's a p-series with p equals to 2. And yes, it's convergent p-series. And recall p-series from my earlier video on infinite sequences and series on the integral, test, and estimate of sum. So here, as usual, I'll put a link to Steam it, and then I'll take a screenshot from my calculus book. It just gets more condensed there. But anyway, so recall this, that the p-series summation from n equals 1 to infinity of 1 over n to the power of p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. And in our case, it's greater than 1. It's p equals to 2, so it's convergent. Yes. So now let's look at another example, example 2, and this one right here. So we know from my earlier video that the alternating harmonic series, which is written like this, summation from n equals 1 to infinity of negative 1 to the power of n minus 1. So if you plug in 1, you get 1 minus 1 is 0, so positive. Then 2 becomes negative, and so on. Negative plus positive, negative, and then divide by n like that. So it's alternating harmonic. So 1 minus 1/2 plus 1/3 minus 1/4, and so on is convergent. And here's again a link to my earlier video. This is why you should also follow my videos in order. Everything will flow much faster. So recall from my earlier video on alternating series. So here's a link to the alternating series on Steam it, and just screenshot from my calculus book. So the alternating series test, recall this one. If the alternating series test, if we're given the alternating series like this, and where this term bn is less than, bn is greater than 0, we just take out the alternating negative 1 there. So if this satisfies this condition right here, where it's decreasing, a bn plus 1 is less than bn, and the limit bn is approaching 0 as n approaches infinity, then the series is convergent. And from example 1 in that video, go over the alternating harmonic series like this: 1 minus 1/2 plus 1/3 minus 1/4 equals this, and the conditions it satisfies. Yeah, it satisfies that it's decreasing, and because you just plug in 1 over n plus 1, because bn would be just 1 over n. And then it's going to be less than 1 over n because that plus 1 there. And also the limit as bn approaches 0 is 1 over n as n approaches infinity. So the series is convergent by the alternating series test. Again, just a recap on that. And if you were to graph these out, so it's alternating. There's the an terms alternating like this. And then the summation or the partial sums, when you're adding these up, it's going to go fluctuating like that. And they're just going to get a limit like that, which is fascinating stuff. And the limit is actually very interesting. It's the exact sum of the series is ln 2. And I also go over that in one of the exercises, not exercise 36. That was from my calculus book, but I used a different numbering system. So anyways, just jump right ahead now. So anyways, yeah, so although the alternating, so the keyword is alternating here, harmonic series is convergent, it is not absolutely convergent because the corresponding series of absolute values is, if you take the absolute values of the alternating harmonic series, what we get is just the harmonic series, which is divergent. So take the absolute value of, let's see what it was again, negative 1 to the power of n minus 1, so you got that right. So negative 1 to the power of n minus 1 divided by n. So take the absolute value of that. So this is going to be n minus 1 over n, like that. And now this, so the negative terms, they're all going to be positive. So it just equals to 1 over 1, or I'll just put 1 plus 1/2 plus 1/3 plus 1/4 plus dot, dot, dot. And yes, as I just stated, which is the this series right here is just the harmonic series with p, or p series with p equals to 1 here. So it's the same thing as 1 over, as the one I illustrated here. So 1 over np, p is 1, and it's convergent if p is greater than 1. But if it's divergent if its p is less than or equal to 1. So as stated over there, and is therefore divergent, and as I've gone over in my earlier videos on that. Anyways, now let's go over to conditional convergence. Yes, conditional convergence, not conference. Anyways, as you can see here, this is conditionally convergent because the alternating harmonic series is convergent but it's not absolutely convergent. So this goes to definition 2. So a series, summation an, is called conditionally convergent if it is convergent but not absolutely convergent. Example 2 shows that the alternating harmonic series is conditionally convergent. Thus, it is possible for a series to be convergent but not absolutely convergent. However, the next theorem shows that the absolute convergence implies convergence. So if it's absolutely convergent, then it is convergent nonetheless, even without the absolute. So if a series summation an is absolutely convergent, then it is convergent. So yes, if the absolute values are convergent, then it is as well. Alright, so now let's look at the proof for this theorem, and it's pretty straightforward. So observe that the inequality, so what I'll do right here is, I'm going to write an. So an can be positive, it can be negative, but now if I add the absolute value of an, this means that, well, this is going to be greater than or equal to 0. Because it can't be negative, because we're adding the same exact absolute value of it. So if this is negative 4, and this is going to be 4. So you can add them, they're going to go to 0. So it's going to be greater than 0, but it's also going to be less than the absolute value if these were both positive. If this was 4 and this is 4, that's going to be 8. So in other words, it's going to be 2 times the absolute value of an. So it's between these two choices. So yes, this inequality is true because the absolute value of an is either an or negative an. So yes, either it cancels or it doubles up. So if the series an, or the summation of an, is absolutely convergent, then that just means that the series, as by our definition, then the series, the absolute value of an, the summation of the absolute value of an is convergent. So then just 2 times that is also convergent. So that's summation from, just summation of 2 times absolute value of an is convergent. So this is convergent, given that this is absolutely convergent. That means absolute value is convergent by definition. Therefore, by the comparison test, and I'll go over that recall from our earlier video soon. So then the addition of these two is convergent. The summation of an plus absolute value of an. And so first of all, recall that the comparison test from my earlier video. And here from my earlier video on the comparison tests, so the comparison test, suppose that the series summation of an and the other series summation of bn are series with positive terms. If the summation of bn is convergent, or the series summation of bn is convergent, and an is less than bn for all n, so all the terms are less than it, then the summation of an is also convergent, and vice versa for if it's divergent. So if the series bn is divergent and an is greater than bn, that means for all n, then summation of an, the series, is also divergent because the terms are bigger. So if the terms are less and less than a convergent series, it is convergent. If the terms are greater than a divergent series, then the series is divergent. And in our case right here, so we have this is an is absolutely convergent. Then that means that by definition that the summation of absolute value of an is convergent. So then 2 times that is convergent, just a constant there. And then this is always greater than or equal to this. So this is a convergent series. So this, it's convergent. So if that's convergent, then this is going to be less than that. So we're going to have a less than a convergent series. That's also going to be convergent. So the series, by the comparison test, an plus absolute value an is convergent. So then what we have is that the series an is just a difference between these two. So in other words, if I write the series an, like that, an, this equals to, this just equals to the summation, summation of an plus absolute value of an, like that. That's just going to be this right here, and then it's just subtracted by a absolute value of an, like that, so that these two terms cancel. But in other words, so then all we're left with is an. But in other words, what we have is this is a convergent series. Convergent. This is also convergent series, as we showed above here. So this summation an plus absolute value of an, this is also convergent. So in other words, we have a difference of convergent series, and a difference of them is going to be convergent. So yes, that's what we have. So what we have is this summation of an of the series is a difference of 2 convergent series and is therefore convergent. So yes, convergence, if this is a limit, for example, L, this is going to be, let's say, L1, L2, going to be just L1 minus L2. and that's going to be a number, or in other words, a limit. So yeah, so it's therefore convergent. So now let's look at another example, and this is example 3, and it states determine whether the series, and we have series from summation from n equals 1 to infinity of cosine of n divided by n squared, which is just equals to cosine 1 divided by 1 squared plus cosine 2 over 2 squared plus cosine 3 over 3 squared plus dot dot dot, and determine whether this series is convergent or divergent. Alright, so let's look at the solution. So my calculus book states that this series has positive terms and negative terms, but it is not alternating. The first term is positive, the next 3 are negative, and the following 3 are positive. The signs change irregularly. And here's just a calculation check to ensure that calculus book is correct. So note that my calculus book used radians for the units for this cosine angle, and my and my OneNote right here that I'm using uses degrees. So I need to convert degrees to radians. And note that half a circle is 180 degrees, which equals to pi radians. So if I put this calculation check as I've done in my earlier videos, I would just type it in here and see if it works, because it's pretty amazing. You can just type it in the OneNote and just automatically calculate. So cosine 1 times, so that's 1 degree, times 180 degrees divided by pi radians. Yeah, so this converts the one, this is actually 1 radian, and converting it to degrees because my calculus book uses degrees. So yes, I believe that's what I said earlier as well. So plugging that in degrees, and then let's press equal, so that's positive. So this is correct. So it says the first term is positive, and then the next 3 are negative. So let's see the next 3. So here, as you can see the calculation, those are correct here. So put 2 times 180 divided by pi, and you can just type pi, and automatically knows what you're talking about. And equals negative. Yeah, so negative, then we get a negative, 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 so that's 3. And then we get 3 afterwards that are positive. And you could type it in as well, and you can just plug in a calculator, it's like calculation check here, it's all in one place. And then, yeah, so we get 3 right here, positive, 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 and then we get a negative here on the 8. This is the radians, 8 radians, or 8 times 180 divided by pi degrees. Yeah, so now we can apply the comparison test to the series of absolute values, and that's because of the nature of cosine or trigonometry. So let's look at the summation of up to infinity from n equals 1, and this is the absolute value of cosine n over n squared. So since we have a n squared, n is always positive over here. So n is always positive. That means the only part that can be negative is the trigonometry, the trigonomic function cosine. So in other words, we can get rid of the absolute value for the bottom. So this just equals to summation from infinity or up to infinity from n equals 1. And this is going to be cosine. Yeah, cosine n, absolute value of cosine n divided by n squared. So yes, the only thing I could change signs is the cosine function like that. Yeah, and now since the absolute value of cosine n is less than or equal to 1, you can remember just the ratio of the adjacent over hypotenuse. Yeah, so it's always going to be just a sine curve like that. I mean the cosine curve like that, where the difference right here to here is going to be, well, this is going to be 1, that's going to be negative 1, like that. So yes, just recall that. So the largest values it could be is 1 or negative 1, or in other words, absolute value of 1. So it's going to be less than or equal to 1 for all n. So that's what we have, is that the absolute value of cosine n over n squared is going to be less than, because this is going to be less than, yeah, the top part is going to be less than 1. And then just divide by n squared like that. So yes, we could start applying the comparison test, because we know that this summation, or the series of, series of this one here, summation 1 over n squared, is convergent because it's just a p series with p equals 2, which is greater than 1. See that p series, recall right here. So p is greater than 1 is convergent. We have p equals to 2 there. So we have all the terms, cosine, absolute value of cosine n, scroll here, oh yeah, all the values of cosine n divided by n squared is less than a convergent series, the terms of a convergent series. Therefore, the series of the summation of absolute value cosine n divided by n squared is convergent by the comparison test. So thus the given series right here, summation cosine n over n squared, is absolutely, when you remove the absolute value signs, it's absolutely convergent, and therefore convergent by theorem 1. So yes, so what we could do is if it's something's alternating like this, we could just find out the absolute value. If it's convergent, then it's also convergent everywhere. So absolutely convergent means it's convergent, but not necessarily the other way around. If it's conditionally convergent, that means the function or the series is convergent, but if you take the absolute value, it might not be, or it won't be if it's conditionally. All right, let's keep going further. Yeah, so now the figure below shows the graphs of the terms a(n) and partial sums Sn of the series in example 3. So notice that the series is not alternating but has positive and negative terms. Yeah, so here, so remember in the calculation here, so we have the first one is positive, the first term, the cosine like this, cosine 1 of 1 radian is going to be 0.54, and then we're going to get a negative, so 3 negatives. So we have, there's the positive, and the an is in blue. And then gets to 3, 1, 2, 3, then we get 3 right here, and then it becomes negative like that. So what we have is, the series not alternating but has positive and negative terms, but then they die out, and then you take the Sn, the partial sums, you can see that there is a limit approaching, because this is going to 0 like that at a fast rate. Alright, so that's fascinating stuff. So now let's go further. So the following test is very useful in determining whether a series or a given series is absolutely convergent. So if we have the limit as n approaches infinity, and we take the ratio of the term, so absolute value of an plus 1, divide this by an, if this equals to L, and this is going to be less than 1. So yes, if we have the scenario, then the series, the summation from n equals 1 to infinity of an is absolutely convergent and therefore convergent. I'll prove this soon. And then the second part of this, you have this ratio test, is instead if we had the limit as n approaches infinity of absolute value of an plus 1 over an. So the terms right here, the ratio of the an plus term divided by the an. If this is approaching a limit equals to L, which is greater than 1. Yeah, so if we have this scenario, then the series summation from n equals 1 to infinity of an is divergent. So if the limit of this ratio, of the absolute value of the ratio is greater than 1, then it's divergent. And if it's less than 1, then it is convergent, or absolutely convergent, and hence convergent. And on the other hand, if we have that the limit, so if we have the limit as n approaches infinity of an plus 1 over an, if this equals to L and this equals to, let's just say it equals to 1 here. Yes, if it equals to 1, then if we have it equal to 1, then the ratio test is inconclusive. That is, no conclusion could be drawn about the convergence or divergence of the series of the summation an. Alright, so now let's look at the proof for this. So the idea behind this, or the idea of the proof for the first part, let's look at I. So we have here limit as n approaches infinity of the absolute value of the ratio an plus 1 over an equals to L. If it's less than 1, then the series an is absolutely convergent and therefore convergent in general. So the idea is to compare the given series with a convergent geometric series, and recall the geometric series, which I'll go over several times in this video. Recall it from my earlier video on infinite series. And the geometric series right here is the summation from n equals 1 to infinity of ar to the power of n minus 1, and then which equals to a plus ar squared, and so on. So we plug in 1 inside here, n minus 1, or 1 minus 1 is 0, so we get r is the power of 0. Yes, we get r is 0, this one got r1, r2, r3, etc. And then and I showed in that video that it's convergent if the absolute value of r is less than 1, and its sum is, we get this here, a divided by 1 minus r, so we can get an exact value of the sum. And if r is greater than 1, the geometric series is divergent. So what we want to do is compare with a convergent geometric series, like that. Let's bold it. So yes, notice that we have here the absolute value of r less than 1, that's convergent for this geometric series. And we have right here L is less than 1 of this ratio. So since L is less than 1, we could choose a number R that's greater than L but less than 1, somewhere in between. And since what we have is, since limit as n approaches infinity of absolute value of the ratio an plus 1 over an, if this equals to L, and we have chosen a number r such that we have L is less than r, and where r is less than 1, so that it fits this geometric convergence series. Yeah, so since this limit exists, it equals to L, and we have L is less than R, the ratio an, or the absolute value of an plus 1 over an, will eventually be less than R. That is, there exists an integer n, so when we're dealing with the series, we've got to get to the right integer that corresponds with R is greater than L there, or this L, which is the ratio, the limit of the ratio is going to be less than R, so they're at some integer n. So what I'll do is write, so there's going to be an n, a capital N, such that the absolute value of an plus 1 over an is going to be less than R. Yeah, since the limit is equal to L, so eventually you're going to have it less than R. L is less than R. R is greater than L and less than 1 there, and or whenever. Again, it's very similar to my precise notation of precise definition of limits. Whenever n is greater than capital N, so there's an integer such that this scenario exists. Yeah, or equivalently, what we could do is just move the an at the bottom to the right side. So again, it looks like that our geometric series. So, or equivalently, we'll have is absolute value of an plus 1, and this one we're just moving it over to that side. It's less than, and it's going to be less than an, absolute value of an times by R, and again, whenever, because we're choosing this R such that this scenario is true. So whenever n is greater than or equal to n. Yes, so we have this scenario now putting n successfully equal to capital N, and then n plus 1 and n plus 2, and the above inequality right here we obtain, and this is a very, very ingenious method by my calculus book. So what they have now is, if they were to write this, replace or add a capital N there, so we have a capital N plus 1, is because that's the n there, we just plug in n, is less than, so we're going to have less than a capital N times by R. And now if we look at this, so this capital integer, this capital N, or this integer capital N that exists such that this scenario is true, so that the next integer right after it's going to be n plus 1, and since there's a plus 1 there, so let's put it here just to make it a bit more easy to follow. So we're going to have an a n plus 1 now. So we have an a n plus 1 times it by R. This is going to be greater than a n plus 1 plus 1. So it's going to be plus 2, like that. And now this an plus 1 is over here. So this is just this. This whole thing is that. It's just, I mean, that's our an plus 1, which equals to this whole thing, which equals to an times absolute value of an times R. So this is equal to, well, this. So in other words, this equals to, or I mean, it's less than. So this right here is going to be less than, so an is going to be absolute value of an times it by R, and then there's an extra part in there. So that's just this right here. So I'll write it out fully for, so this is this, and this is also this right here, times it by R. And this equals to, I'll just write it out fully for the first time. So a capital An times R squared. Alright, so now continuing this trend, what we have for the next one, when we, so we have from a capital N, then we have a capital N plus 1. So the next one, just go in order, a n plus 2 there. So a capital N plus 2 times it by R, and it's going to be, it's going to be greater than, and again, follow this exact same pattern. So capital N plus 1, I mean n plus 2 plus 1 is going to be 3. So a n plus 3, absolute value like that. And now this is, so this part right here, a n plus 2, that's just this right here. Yeah, we have a n plus 2 is right here. That's this right here. Actually, I'll put an arrow like this. So this like that. So it's going to be less than an plus 1 times R, which is all the way over here. Just simplified all the way there. Absolute value of an times it by R squared. So put a better bracket like that. and then this goes all the way there. So then what we have is this is going to be less than, because it's replace an plus 2 with this right here, so it's less than that figure there. So it's going to be absolute value of an times r squared times r. It's going to be r cubed, like that. And then keep going on and on, so dot, 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 and then we get in general, so in general, yeah, so in general is right here, capital N plus, I'm going to write K, the absolute value of it is going to be less than, then we just write this all the way down to the right side there, so this is going to be A capital N, A of capital N, times by R K, like that. And I also just forgot to write for all K greater than, for all K is greater than or equal to 1. So yes, we have K is equal to 1 there, then 2, 3, 4, and keeps going on and on. So that's what we have. So now the series, now the series right here, summation from infinity or up to infinity from n equals 1 of, and let's write this down right there, of absolute value of A capital N R K, like that. This is equal to, when we sum this out, so when n is equal to 1, we're just going to have, actually, yeah, not n, K, like that. So when K equals to 1, this absolute value of an, that doesn't change, A capital N, like that. We're going to have r to power of 1. So yeah, r1 plus A absolute value of an, r2 plus absolute value of A capital N, r3 plus dot, 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 dot. Yeah, now this series is convergent because it is a geometric series with r is greater than 0 and less than 1. So again, recall geometric series right here. So we have if absolute value of r is less than 1, and we have this scenario a, r, n minus 1, and so on. And yeah, note that just for detail, and this says n minus 1 there, but doesn't really matter. Ours is just right here is k, like that. There's no minus 1 there, but that just means, yeah, that just means in our case here, a is equal to just a by itself. But here we could just work it around, show that it's exactly the same thing. We could have this is going to be our a, and then our r is going to be, yeah, for example, another one, r is 0. That's just be 1. So then this one we could take a n r. Just for completeness, we can have, this is going to be a capital N, yeah, so a equals to capital, absolute value of a capital N times r, and then times this by r1, so that, this becomes r1. Or worded better, let's just undo this and that. We could just make this a 1. So this is going to be our a, then times it by r1. So there it is, yeah. This could be our 1, and times it by r2, and this could be our a. And so on. So yes, you can see the pattern. So that is a geometric series. I'm just going to remove this. Just wanted to go over that quickly to show you that it's one and the same. Yeah, so yes, that's convergent geometric series. So now the general inequality above, I'll put general right here, underline this general right here. So a capital N plus k is less than this geometric series, absolute value of an times rk for all k is greater than or equal to 1. And together with the comparison test shows that, and what we could do right here is I'm going to write the absolute value, the summation from n equals 1 to infinity, actually not n equals 1, n equals 2, I'm going to go from right here. Yeah, I'm going to go right from here. So this is the general inequality, an plus k. So what I'll do is, and we're going to start off with k equals to 1. So I'm going to go n equals to capital N plus 1 of the absolute value of an. This is going to be equal to, and then we could write this as, yeah, just to rearrange it. So that this is like that, so that we have now k equals to 1 up to infinity, and we're going to start off with, this is going to be the same thing as a, replace this with n plus k, capital N plus k. So yes, this right here is equal to, yeah, just writing it this way, just so that we could write a n plus 1 plus a n plus 2. And again, because it doesn't matter where we start off with, because remember, for infinite sequences or terms, infinite series, we just want to know what happens as n gets large. Doesn't matter what it is for a finite number of terms. So n plus 3, absolute value, then plus dot dot dot. Yeah, so thus this is also convergent because of the comparison test, because these terms are less than a convergent series' terms. So so an plus k, like that for k, is greater than 1. So it's also convergent. It follows that the series, even from n equals 1 to infinity, of absolute value of an is convergent. And recall that a finite number of terms doesn't affect convergence. So here we're starting off of capital N plus 1 because eventually we're going to have a number whenever n is greater than or equal to capital N, like that, such that we have this scenario where the ratio of an plus 1 divided by an, the absolute value of it is less than r. And because we just chose that scenario because the limit exists and it equals to L there, where we're given L is less than 1. So we just choose a number r, and we're going to get terms capital N like that. Work around with it, we're going to get a geometric series, and that geometric series is going to be convergent, and then all the terms of an plus k are less than it, so then that's going to be convergent, and that is just the sequence that we're dealing with, but for n is equal to n, capital N plus 1. So yes, that's a mouthful. So yes, therefore the series of the summation of an is absolutely convergent, and therefore convergent, because it's absolutely convergent means it's also convergent in general. Alright, so now let's look at the second part of the ratio test, and let's scroll up here, and it says if the limit right here, above here, if limit as n approaches infinity of absolute value of an plus 1 over an, the ratio, the absolute value of it equals to L, and it's greater than 1. And also, I forgot to state right here, or if we had also, this is the more generic, this is the more trivial one, where the limit as n approaches infinity of the ratio an plus 1 over an, if this equals to, well, infinity. Then in this case, series also divergent. So I just forgot to write that down earlier, and so pardon me there. So if we have, let's write that down again. So if we have limit as n approaches infinity of the ratio an plus 1 over an absolute value, if this is equal to L greater than 1, or or limit as n approaches infinity of ratio absolute value of an plus 1 over an, if this is equal to infinity. Yeah, then what this means is that the ratio, the absolute value of an plus 1 over an will eventually be greater than 1. That is, there exists an integer capital N. Again, this is my calculus book uses this all the time. It just stems from the precise definition of limits, and it's very interesting. It's pretty much writing generally abstract statements in direct mathematical ways right here. Yeah, so if we have this scenario, it's going to be the scenario where this ratio right here, so we're going to have this absolute value, I'll make it bigger, absolute value of an plus 1 over an, like that. This is going to be greater than 1 eventually, and this is whenever, and we're going to choose, whenever n is greater than or equal to some integer n, capital N, like that. So eventually that's going to happen because we know that the limit is greater than 1 or goes to infinity. In either case, it's going to be greater than 1 eventually. Remember, when we're dealing with infinite series, all that matters is what happens eventually, as in when things get large, when n gets large, when it approaches infinity. And now what this means is, well, as before, we could do is move this bottom part over to the other side. So this means that we're going to have an an plus 1. Move it over to the other side. An times 1, that's going to be, this is going to be greater than absolute value of an, like that. And this is whenever. So eventually we're going to have a scenario that n is greater than, whenever n is greater than capital N, then we're going to have this scenario where an plus 1 is going to be greater than an. In other words, the terms are increasing. Yeah, and so what we have is they're increasing like that. So by the test of divergence, so limit as n approaches infinity of an right here, this is not equal to 0. Yeah, so this is equal to 0. It's not equal to 0 because it's increasing, i.e. I'll just write an is increasing. like that eventually. All right, increasing increasing as n gets large, as n goes to infinity, because we're going to have a scenario where n is greater than capital N, and it's going to be greater than the previous term. So it's going to keep going bigger and bigger. So in other words, it's not approaching 0. So therefore, the summation an, or the series an, diverges by the test for divergence. And recall the test for divergence also from my earlier video on infinite series and that geometric series and so on. The test for divergence, if limit as n approaches infinity of an does not exist, or if limit as n approaches infinity of an is not equal to 0, then the series and from summation from n equals 1 to infinity of an is divergent. So recall from that. So now let's look at part 3 of this ratio test. And note, part 3 of the ratio test says that if, and let's just scroll up here, where is it? So that's right here. So if limit as n approaches infinity of the ratio an plus 1 over an, absolute value of this ratio equals to 1, then the ratio test is inconclusive. That is, no conclusion can be drawn about the convergence or divergence of the series an. So let's write this down. So it says that if we have limit, let's write that down again, limit as n approaches infinity of an plus 1 over an, if this equals to 1, like that. Yeah, so this says if it equals to 1, then the test gives no information. So for instance, for the convergent series, remember it's convergent P series where n is equal, P is equal to 2, which is greater than 1. We have, so if we take the ratio of this one right here, an plus 1 over an, let's simplify the ratio before we take the limit. So we have, this case, we're going to have 1 over n plus 1 squared over 1 over n squared, like that, and just move this over to the top. This equals to n squared over n plus 1 squared. Now I'm going to do is multiply the top and bottom by the highest power, which is n squared, like that, n squared. So this would cancel, that equals to 1. Now at the bottom we're going to get a, this, we can move it inside the bracket, so this would cancel. So we have a 1 plus a 1 over n, like that, squared. And now we take the limit, so limit as n approaches infinity of this ratio right there, 1 plus 1 over n. And also, yeah, I forgot to note, so this is absolute value, but this is n plus 1, everything's squared, so then this is always going to be positive, so you don't need to do absolute value there, because we're squaring it anyway. So when you square negatives, it becomes positive, so yes, it's always going to be positive there. So 1 over n, so this here we're going to get a 1 over infinity, which approaches a 0, so in other words, we're going to get a 1 over 1, this equals to 1. So this is a convergent series, and it equals to 1 there. And now, whereas if we looked at the divergent series, or the divergent harmonic series, or P series, where P equals to 1 of the summation of 1 over n, we have, so in this case here, we're going to have an plus 1 over an, the absolute value of this ratio. This equals to 1 over n plus 1 over 1 over n. Move this over, so we're going to get a n over n plus 1, divided times it by, multiplied by top and bottom by 1 over n over 1 over n. This equals 2. This cancels. 1 over this n over n cancels, and we're going to have 1 plus 1 over n. And now this limit as n approaches infinity of this ratio of 1. Yeah, and again in this case here, we have n is always positive. So we have n is going to be 1, 2, 3, 4, all, etc. So there is no negative values anywhere. It's no subtraction. So this is, we can remove that absolute value. So this equals to 1 over 1 over 1 plus 1 over n. This goes to, again, 1 over infinity goes to 0, and remove that, equals to 1 over 1. This equals to 1. So in other words, we have a divergent series where the ratio an plus 1 over an, the absolute value of it is equal to 1. And we also have a convergent series that has it equal to 1. And in mathematics, all you gotta do is find one contradiction and you're done. And that's actually how I apply my mathematical skills to my gyro experiments. If you've been watching my gyroscope experiments in my earlier videos, which are pretty epic stuff. But anyways, so yes, so you could you could easily debunk all of physics just by finding a contradiction. Yes, so therefore, if the limit as n approaches infinity of the ratio an plus 1 over an, the absolute value of this ratio equals to 1, the series, the summation of an, might converge or it might diverge. In this case, the ratio test fails and we must use some other test. Alright, so now let's look at another example, and this is example 4, and this one states test the following series for absolute convergence. And we have here the summation from n equals 1 to infinity of negative 1 to the power of n times n cubed over 3n. So again, we have an alternating series here because of this negative 1 to the power of n. If n is 1, if n is 1, we're going to get negative 1. That's an odd power. If n is 2, this is going to be even. That's going to be positive 1. So it goes from negative 1, positive 1, negative 1, positive 1, etc. Alright, so thus we could use the ratio test right here, and this is with, we're going to let an equals 2, and this one is just the sequence inside. So negative 1 to the power of n, and then n cubed over 3n, like that. So the ratio test, let's just look at this again. So all we're going to do is take the limit of the ratio of an plus 1 over an and see what we get, and see if we can determine if it's absolutely convergent or not. And let's just jump right in. So we have this equation. So we're going to take the limit, but I'll just write this out first. Let's just see what we can simplify this. So an plus 1, an plus 1 over an, like that, absolute value equals 2. So this is going to be a giant formula. So the absolute value, then we're going to have the negative 1 over there. Let's put this down here. Negative 1 to the power of n plus 1. Here, just moved it down a bit. So now we're going to have n plus 1 to the power of 3. And then this is going to be, divide this by 3n plus 1. Like that. All divide this by. And then now we're going to write absolute value like that. And then just plug in n. Yeah, so what we get now is just this term an. And that's going to be negative 1 to the power of n times by n cubed over 3n, like that. So now that we're taking the absolute value, and notice that, n is always positive integer. So then the only parts that can be negative are these terms right here, the alternating terms of negative 1 to the power of n plus 1 and negative 1 to the power of n, and then absolute value just makes it all positive 1. So we could remove the absolute value, so then this equals 2, and I'm going to do is move this in the center, so that's more in line with this right there. So this equals 2, and then just remove those, and it's going to be now, the top part's going to have an n plus 1 cubed. Then we're going to have at the bottom 3n plus 1. And now here, this is dividing by n cubed. We just put that at the bottom here. N cubed. And we're dividing by a division already, so this one goes on top. That's going to be 3n. Alright, so now we could simplify this further. So this right here, well, we have this 3 to the power of n plus 1. If that's at the bottom, then there's 3n there, so we could just combine the powers, the same base, and put it at the bottom so that we'll subtract n from n plus 1. So then this equals 2. So the bottom is going to be 3n plus 1 minus n there, so those just cancel, becomes a 3. So let's put that 1 like that. 1 over 3 times, so we get rid of these two parts. So yeah, we could just cancel this, and that goes at the bottom. And then times it by, then the top part here, these are the same powers, power of 3, so we can just combine those. It's going to be n plus 1 over n, power of 3. And yeah, just simplify it further. So 1 over 3, n plus 1 over n, 3, like that. Now, before I take the limit of this, I'm going to simplify this further. As always, when dealing with limits like this, what we could do is multiply the top and bottom, or divide the top and bottom by the highest power. In this case, when you put this inside, it's going to be n cubed. So 1 over n cubed, times it by that, and then, so times it by 1 over n cubed, divided by 1 over n cubed, so not changing anything. And then what happens here is, this can go inside, and that'll just become n. So this becomes like this, 1/3. Then this becomes, divide this out inside, it's going to cancel with this, and this is going to cancel. And we're going to left with, it's going to be 1 plus 1 over n over 1 power of 3. And now, so we could take the limit here, so limit as n approaches infinity of this ratio there, that just equals to this right here, so 1 over 3, 1 plus 1 over n, power of 3, like that. So you're dividing by 1 doesn't change anything. Let's put an n like that, and 3, and then now this one goes to, well, 0. It goes to 1 over infinity, which approaches 0, so what we're left with is going to be 1 over 3 times 1 to the power of 3, that's just 1 over 3. So this is 1 over 3, in other words, this is a limit, and this is less than 1. Remember the ratio test, scroll up to the ratio test, and we have here, if it's less than 1 in the series right here, an is absolutely convergent and therefore convergent. So yes. We've just proven it is absolutely convergent. Yeah, so thus by the ratio test, a given series is absolutely convergent and therefore convergent in general. So yes, fascinating stuff. So note on estimating sum. So in my earlier videos, we used various methods for estimating the sum of a series. The method depended on which test was used to prove convergence. But what about series for which the ratio test works? There are two possibilities for this case. If the series happens to be an alternating series, as in example 4, then it is best to use the methods of my earlier video on alternating series. So yes, if it's an alternating series and the ratio test works, just use the methods in my earlier video. But if the terms are all positive, then we can use the special methods explained in exercise 1 later in this video. So yes, stay tuned for that. Alright, so now let's look at another example, and it's example 5, and it states test the convergence of the series, and we have the summation from n equals 1 to infinity of n to the power of n divided by n factorial. So, and remember n factorial is just 1 times 2 times 3 times 4 times 5, etc. Alright, so let's look at the solution for this. So since the terms an equals n to the power of n divided by n factorial are all positive, yes, so n is a positive integer, n to the power of n is positive, n factorial is all positive. We don't need the absolute value signs when we're looking at the convergence test. So basically what it means is absolute value of an plus 1 over an, this just equals to, well, we don't even need that absolute value there. This just, equals an plus 1 over an. Let's write that here, an plus 1 over an in our case. This just equals 2, so let's plug in n plus 1 there. So we're going to have an n plus 1 to the power of n plus 1 over n plus 1 factorial. And now we're going to divide this out by n over n to the power of n divided by n factorial. But that just, remember, just the bottom part gets switched to the top. So this just becomes at the bottom n to the power of n. Then the n factorial goes on top. So you're dividing by a division like that. So we have this. So now what you could see is we can do some cancellations. And this one's actually, if you can just use the definition of factorials, this right here, n plus 1, this includes an n factorial there, and we have also an n plus 1 there. We can cancel on the above. So we could write this as equals to n, just write this n plus 1. Right here, I'm also going to separate this right here. So this n plus 1 to the power of n plus 1 is just equal to n plus 1 like this, times it by n plus 1, so the power of 1, n plus 1 to the power of n. Just so that when you combine them, they add up. So I'm going to separate it like that, times by n factorial. And then the bottom part is going to have like this. So now what we're going to have is, I'm just going to move, actually I'll just leave it there. So this n factorial equals to n plus 1 times it by n factorial. So in other words, this right here, it equals to n plus 1 times n Yeah, times n n minus 1 times n minus 2 dot 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 all the way into 2 times 1, etc. like that. Whereas this part right here, this just equals to n factorial. So we can just write this as n plus 1 times n factorial, and then just times this by n to the power of n. So yeah, that's what we have here. So what we have now is this cancels, this cancels, this cancels, this cancels. So now what we have is n plus 1 to the power of n divided by n to the power of n, and we can just combine these together because the powers are the same. So then this equals n plus 1 over n like that. And now just divide this out. This equals to 1 plus, and then 1 over n like that. So now what we have a very interesting limit right here when we take the limit. So the limit as n approaches infinity of 1 over 1 plus n to the power of n. Well, what we have is a scenario of, because this one is a bit hard to, yeah, you can't just plug it in because you have there's a division by infinity and there's a power of infinity right there. Scenario of and I'll just write this down, of a 1 plus 1 over infinity to the power of infinity. So now you have multiple infinities here. This one's approaching 0, but during that whole time, it's still incrementing greater than 1, and there's power of infinity. So then, scenario of this, what is going on here? All right, so now this limit is actually one that I covered earlier. So now let's use the power of my ability to recall earlier videos. So recall from my earlier video that this is in fact the number e written as a limit, which is absolutely fascinating. So here's a link to my earlier video on it, and here's a screenshot from my calculus book on the number e as a limit. So we have shown that if fx equals ln x, then derivative equals 1 over x. Using that and using the definition of derivative, I show that derives this formula right here, e equals the limit as x approaches infinity of 1 plus x to the power of 1 over x. But then you just replace this x with n equals 1 over x. Yes, so that we have this limit, which is the same one that we just have. So we have the e is equal to the limit as n approaches infinity of 1 plus 1 over n to the power of n. So absolutely fascinating. You plug in a calculator and you see that this is approaching the famous 2.718 number. So going further, yeah, so and also in this, I just want for completeness, so then by theorem 2.5.8 and the continuity of the exponential function here, just want to put a reference where I got that. So the theorem 2.5.8 mentioned in the above proof is shown in my earlier video as well. Hashtag earlier videos, just for completeness. For reference for later, and that's basically here. If f is continuous at b and limit g of x, limit as x approaches a of g of x equals to b, then the limit x approaches a of f of g of x. So in other words, we have a composite function where we plug in this function inside this function. This equals to f of b. So then the limit, so when you have a limit like this, you could plug the limit inside. So the limit of f of g of x is equal to the limit of equals to f of the limit of g of x. So yes, fascinating stuff like that, and they use that in here. So you could plug in when you take a limit, you could plug that inside the function at the exponential as well. So anyways, going further, yeah, so yeah, this theorem says that a limit symbol can be moved through a function symbol if the function is continuous and the limit exists. In other words, the order of these symbols can be reversed. So you can put the limit inside, outside, depending on where the x variable is that you're taking a limit towards. And again, which I use this theorem throughout my videos. Anyways, I just want to put that for reference. So now, so that's what we have. It equals to e. So thus, the limit as n approaches infinity of 1 plus 1 over n to the power of n equals to e. And e is, well, greater than 1. This equals 2.718, etc. And since e is greater than 1, the given series is divergent by the ratio test. Remember, this was part b, if it equals to infinity or greater than 1, yeah, or a limit greater than 1. Let's just scroll up here. So this is the second part. So if the limit is equal to L, greater than 1, then the series is divergent. So it is divergent. So that's fascinating stuff. And it equals to number E. And yeah, I recommend checking out my earlier videos on those theorems and showing that the limit is equals to E. Alright, so now I want to make a quick note on the ratio test. Although the ratio test works in this example 5, that I took the ratio of the limits and so on, show that it equals to e, and which is greater than 1. An easier method is to use the test for divergence and recall the test for divergence. Let's see where I put a recall of my recall. So the test for divergence, if the limit n approaches infinity of an does not exist, or if the limit is not equal to 0, so if it does exist and not equal to 0, then the series right here, an, is divergent. So we could use the test for divergence instead of taking the ratio test. So yes, just because we have the ratio test does not mean it's always best to use that or quickest or easiest to use it. Yeah, so since what we could do is, right, well, we have an right here. So an is just equal to, recall, that's just equal to n to the power of n divided by n factorial. So we have this equals to n to the power of n over n factorial, and now this just equals 2. So the top part right here, this just equals to, well, n times n times n times yeah, dot 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 and dot dot dot. This keeps going all the way up to here, so n times. So we're gonna multiply this by n times n times n all the way to n terms, and then the bottom right here we're gonna have also n terms, but it's gonna have it's gonna be numbers. The n factorial is gonna be 1 times 2 times 3 times 4, etc. So we'll put a 1 here, and this left side 1 times 2 times 3 times 4, etc. 5 6 7 dot 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 all the way until times 10. Yeah, now this right here is, well, this is going to be greater than n, and that's because, well, if this n right here are greater than or equal to n, if assuming it's not equal to 1. So if you have n right here, so this number right here is going to be n over 1, so it's going to be, so that's equal to n there. Now here we're going to have n over 2, which is, which equals to 1 or greater than 1. And so on and so forth all the way to here. This is the only part where they cancel, is when it equals to 1 here. So in other words, it's going to be greater than this right here, n over 1. So this is going to be greater than or equal to n. Yeah, in other words, this right here is not going to be equal to 0. So yes, it's not approaching 0 by any means. So it follows that an does not approach 0 as n approaches infinity. Therefore, the given series is divergent by the test for divergence. It's not equal to 0. Alright, so now let's look at another test, and the following test is convenient to apply when nth powers occur. So if you have something to the power of n, such as this n to the n there, it's convenient to use this root test. So its proof is similar to the proof of the ratio test and shown in exercise 2 later in this video. Just the way my order of my calculus book does it. It gives the root test, goes over an example, and then in exercise 2 or later exercises, it has the ratio test. The root test proof. And so yes, I'll prove it later in this video. So let's go over the root test. So if, so part A of it, and it's again very similar to the ratio test. So if we have the limit as n approaches infinity of the nth root of absolute value of an, and remember the nth root, not to be confused with square root, because that's just the second root, or the 2 root or square root, or that's part of 1 over 2. So in other words, this equals to an to the power of 1 over n, like that. So the absolute value of it. So again, when we have an or when we're dealing with nth power like this, so we can try to cancel those out. That's using this root test, so 1 over n. So if this equals to L, which is less than 1, and again, very, very similar to the ratio test, then the series right here, the series from n equals 1, make the subscript, to infinity of an is absolutely convergent and therefore convergent in general. And likewise to the ratio test, if we have instead, if the limit as n approaches infinity of the nth root of an, if this equals to L and it's greater than 1, or if we have limit, this is does not equal to L, it just goes to infinity, but nonetheless still greater than 1. Limit like here, this is limit n as n approaches infinity of the nth root of absolute value of an, like that. If this equals to infinity, so if f approaches infinity, in either case, this is going to be divergent. Yeah, so then the series right here, summation from n equals 1 to infinity of an is divergent. And likewise for the third part of the root test, if we have this equals to 1, so limit as n approaches infinity of the nth root, absolute value of an. If this equals to 1, and then we have it's inconclusive. So yes, I wrote it right here. So then the root test is inconclusive. So in other words, if the limit as n approaches infinity of an to the power of 1 over n, or the nth root, then part 3 of the root test says that the test gives no information. Again, very similar to the ratio test. In fact, yeah, pretty much the same. So the series right here, summation of an could converge or diverge. Yes, doesn't have to... Or, I mean, it doesn't give any information, so yes, it could diverge or converge, and I'll go over a proof of this in exercise 2. Yes, exercise 2 later in this video. So, yeah, also some more notes. If L equals to 1 in the ratio test, then don't try the root test because L will be again 1. Because, yes, once I prove that it's also 1, I'll make this bold. Because remember, both of these, if it equals to 1, it can't give any information. And if L equals to 1 in the root test, so it doesn't matter which one you do first, you know the answer is going to be 1 on the other one as well. Don't try the ratio test because it will fail too. In other words, it's going to get equal to 1, and you're not going to have any information from either of the tests. So yes, fascinating stuff. So now let's look at an example on this. So example 6, and it states test the convergence of the series, and we're given here the summation from n equals 1 to infinity of 2 to the power of n plus 3 divided by 3n plus 2 all to the power of n. So it's to the power of n, and that's convenient for us because we can just apply the root test. Because remember, as I stated, it's good for the nth root. So the root test, we just take the nth root and of the absolute value of that term, and then take it to infinity. So let's see what we have in this case. So what we have is the nth root of absolute value of an, and an in this case is just that in the center there, or this whole thing there. This equals to now. This is going to be, this is going to be the nth square root, the nth root, not square root, nth root of, I don't like using this giant root sign, 2 plus 3 over 3n plus 2 to the power of n. Remember, these just cancel because, let's make it for completeness, this is the same thing as writing 2 to the 3 over 3n plus 2. And this is the same thing as writing like this. This is to the power of n, and then to the power of 1 over n. So power of 1 over n. In other words, we just have an n over n, so these just cancel. So yeah, so it's cancel, so we're left with, so we're just left with the term inside. 2n over, 2n plus 3 divided by 3n plus 2, like this. And now, as always, to prepare for the limit, I'm going to multiply the top and bottom by 1 over the highest power, in this case n, divided by 1 over n, like this, so it doesn't change anything. Plug this into the limit, or actually simplify this first. This will cancel out. We'll have a 2. The n's cancel, then we'll have a 3 over n, over 3, and then n cancels with this, and then plus 2 over n, like that. So then we take the limit of this. Limit as n approaches infinity of this nth root of the absolute value. And also, since we're dealing with absolute value right here, this is the absolute value of it, and this is power of n. Everything is positive, so then we can just get rid of it. Everything is, just positive. So this goes, it's gone. So we just remove it. So yes, because everything is just dealing with n is positive, and there's no way of getting a negative, so that's just positive. The absolute value is the same. So we have the limit right here of 2. So limit of... don't need a bracket. Let's put a division like this. 2 plus 3 over n, then 3 plus 2 over n. So now right here, this is going to be a 1 over infinity, which approaches 0. Likewise here, a 1 over infinity approaches 0. And in other words, this is going to be equal to 2 over 3. So this is equal to 2 over 3, which is less than 1. So yeah, it's fascinating stuff. So this is going to be absolutely convergent. Yeah, so thus this series converges by the root test. Yeah, it's fascinating stuff here because it's less than 1 there, as I stated here. And again, I'll prove that in exercise too. So let's go over last part of this before I get to the exercises. And this is on rearrangements. It's actually very, very fascinating. I wasn't too well accustomed to this before making this video, but it's very fascinating stuff. So the question of whether a given convergent series is absolutely convergent or conditionally convergent has a bearing on the question whether infinite sums behave like finite sums and not. Yeah, they don't always. If we rearrange the order of the terms in a finite sum, then of course the value remains unchanged. But this is not always the case for an infinite series. By a rearrangement of an infinite series an, we mean a series obtained by simply changing the orders of the terms. So it's actually pretty fascinating when you think about this. So for instance, rearrangement of an could start as follows. So we could write this one out as a1. So we could just write this down as, yeah, so a1 plus, we'll go a2, and then let's just jump to a different one so we can go a5. So we have a rearrangement now. Instead of a3, we have a5. Then let's put a3 here. Then let's say we have a4 here, and let's even jump further to a15. And then keep going further, we have a6 plus a7, and so on. So we could just keep going on, and let's add another one, a20. So we could add a1000 if we want. Or in fact, since we're dealing with infinity, I'll just put one for just to illustrate the point. So we can go to a 9 million, a 9,000. Like that. So we just go, because we're going to infinity right here, so plus dot dot dot. So we could bring in any term we like for whatever purpose we want to determine. And again, this makes the summations not exactly like finite sums, because finite sums, you're always going to be the same thing in rearrangement. Infinite sums, we can pull out terms from anywhere, and I'll show you what changes. Yes, going further, so it turns out that if the summation or the series of the summation an is an absolutely convergent series with sum s, then any rearrangement of the summation an has the same sum. That is pretty straightforward, because if the sum is s, it doesn't matter where the terms are, it's always going to be s. However, any conditionally convergent series where you're going to have some negative signs there that make it conditionally convergent, but not absolutely convergent. In other words, the terms that, as I'll show later, are divergent, but when you can make them such a way that they're conditionally convergent, where they cancel out, can be rearranged to give a different sum. So to illustrate this fact, let's consider the alternating harmonic series. Remember the alternating harmonic series? It's a p series of p equals to 1, but it's alternating. So we have 1 over, then 2, 1 minus 1 over 2, plus 1 over 3, minus 1 over 4, plus 1 over 5, and so on. And let's keep going. So minus 1 over 6, plus 1 over 7, minus 1 over 8, and then this keeps going indefinitely, dot, dot, dot. And in fact, this equals to ln 2, as I showed in my earlier video. And recall that this summation is proved in my earlier video on alternating tests. And this one here, recall that this is from exercise to use the following steps to show that this summation, this is the alternating harmonic series, equals to ln 2. Yeah, there wasn't a screenshot of, or a good screenshot of the solutions manual from the calculus book, so I just put it just from here from the question. So just to go check it out, I prove it that it is ln 2 over there. So this equals to ln 2, this alternating harmonic series. Remember, the harmonic series itself, if they're all positive, is going to be divergent. Otherwise, it goes to infinity. So now, if we multiply the series by 1 over 2, what we end up having is, yes, if we have 1 over 2 right here, so this 1 is going to be 1 half. So we're going to have a 1 half. And then now this negative 1 half, that's going to be 1 over 4, like this. 1 over 4. And likewise, here is going to be 1 over 6. And now this one right here is going to be negative 1 over 8. So you can see the pattern right here. So 1 half minus 1 4 plus 1 6 minus 1 8. And it's likewise going to go 1 over 10 and so on. And this keeps going on and on. So so let's do one more subtraction. This is going to be minus 1 over 12 plus dot dot dot. And then this equals 2. Well, the sum is ln 2. Now what we're just going to do is, the sum is going to be divided by 2. So we're just dividing the sum by half. So we're not changing anything else. So this is going to be half of ln 2. Alright, so now next step is if we insert zeros between the terms of the series, what we end up having is, so in this one right here, what I'm going to do is I'm going to just, all we're doing is basically shifting this, so adding the zeros won't change anything. So 0 plus 1/2 plus 0 minus 1/4, then plus 0, and then here we're going to have a plus 1/6. Then plus 0, and then minus right here 1/8, like that. And this keeps going on and on. This equals to 1/2 ln 2. So we're not changing anything. So yes, the zeros again, it doesn't change the sum, so it's going to be the same thing, 1/2 ln 2. So note that adding these zeros does not affect the sum of the series, and each term in the sequence of partial sums is repeated, but the limit is the same. So yeah, my calculus book write that note, but basically what it means is if this is S1, partial sum S1 is 0, then right here we're going to have partial sum S2 equals 1/2. And then afterwards, it's all going to just get repeated. So then at this term here, S3, so we haven't increased the sum, so the partial sum is going to be 1/2 as well. So it just repeated there. So let's put this bold, repeated, and likewise right here, we're going to have, here's going to be minus 1/4, so common denominator 4 multiplied by 2. So 2/4 minus 1/4 is 1/4. So S4 here is going to be 1/4. Then here's S5, which is adding a 0, so it doesn't change anything. And so all we're doing is just repeating the partial sum, but it's all approaching the same thing, which is 1/2 ln 2. This is going to be 1/4, and so on. So here we're going to be the same thing, keep going on and on, dot, dot, dot. So now going further, so now we add the series 1 and 2 using the theorem also from my earlier video on infinite series. I'll get to this theorem in a bit. And the series 1 and 2, I'm going to call this one right here, the generic alternating harmonic series, as 1. So that's series 1. Then the one we just modified and added zeros, so divide by 2 and added zeros. This one we're going to call this series 2, like that. So we're going to add those up and see what happens. And using this theorem right here. So recall from my earlier video on the infinite series that this right here, make it bigger. So theorem, so if we have the series AN and BN, if they're convergent series, then so are the series where we add a constant times AN. So we'll see as a constant, and also the addition and subtraction. So if you were to add these up, in our case we're going to add them, so AN plus BN, they're two convergent series. So this one's convergent 1/2 ln 2, this one's convergent ln 2. Add those up, we're also going to get a convergent series. So the series right here, the summation of AN plus BN is equal to the summation AN plus the summation BN. So we just add these sums. So thus what we end up having is, and I'll write this down as series 1. So let's write series 1 first, which is the alternating harmonic series. 1 minus 1/2 plus 1/3 minus 1/4, and so on. So we're going to have a 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8. Let's go to stick to 8. Dot, 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 all the way, and this equals to ln 2. So now what we're going to do is I'm going to add the second series, so plus series 2. So let's look at the series 2 right here. That's just with the 0, and we divide by half. So now this one you're going to have 1/2. There's a minus 1/4 plus 1/6. So we just go by even numbers every single time, because of the odd ones become positive because we're dividing by 2. So 5 becomes a 10 there, and 3 becomes a 6. So what we end up having here is plus, there's a 0 in front, so put a 0, plus 1/2, and plus this 1/2. So notice what we have here, when we add them, this plus 1/2 would cancel, and then we're going to have a plus a 0, and then minus 1/4. So what we end up having in this case, we have this and this cancel, but this and this multiply. So this right here multiplies by 2 there. So, and then right here we're going to have another 0, plus, and then we're going to have a plus 1/6, like that. So again, these would cancel, and then we're going to have a plus a 0. So we cancel, this comes down, so what ends up happening is this gets down, we get a cancellation, this goes down, and this one adds up. So I'll go like this, plus, and then goes down here. Or better yet, I'll do a times 2. So this is a 1. This is going to be a 2 times. So we're just going to be 2xing on this going down, like that. And then this right here is going to be a minus 1/8. So we bring down, and then we cancel, and then we bring down again, then we times 2. Then we times 2. And so on. And then plus dot dot dot. And then this equals to 1/2 ln 2, because that's just equation. That's just a series 2 over there. So now that we have this, what we're going to do is sum this up. So this equals 2, or sum up a big line like this, equals, so now this 1 plus 2 series equals, so we bring down to 1, we're going to get a 1, and then we're going to cancel this right here, we're going to bring down to 1/3, so we're going to have a 1/3, we're going to have, let's put this 1/3 right here. Then we're going to have right here this 2x's, so that's 1/4 times 2. So this minus 1/4 minus 1/4 is going to be 2/4. In other words, that's going to be 1/2. That's going to be minus 2. And then we bring down this 1/5, so we're going to get a plus 1/5, like that. Or better yet, I'll just put this all in order. So this is going to be 1 plus 0. Then here's going to be 1/3. This is going to be negative 1/2. Now we're going to have a plus 1/5 right here. This cancels, so we're going to get a 0. This right here is going to become a 1/7. And then this right here times 2. So 1/8 times 2 is going to be 2/4. So it's going to be 2/8 or 1/4. So minus 1/4, like that, and so on. And this goes plus dot dot dot. And now when we sum these up, remember by Theorem 2, it just the summation of these series is equals to the summation of the individual sums there. So this is going to equal 2. Ln 2 plus 1/2, that's going to be 3/2. So the common denominator 2/2. So we're going to get a 3/2 ln 2. And now here's some amazing stuff we could do here. So this right here, we can rearrange it. Or better yet, let's just get rid of the zeros. So let's get rid of the zeros. So this equals to 1... Let's put an arrow, so get rid of the zeros to make it better than that. So this is going to be 1 plus 1/3 minus 1/2. So when we get rid of the zeros, it's going to be 1/2, then plus 1/5. And then the 0 is gone, and now we're going to have a plus 1/7. Notice what we have here. We're going to have a 1 plus 1/3, so this is 2 pluses. 2 pluses. And now here we're going to subtract by 1, then we're going to have a plus 1/5, and then plus 1/7. So in other words, we get a 2 pluses. 2 pluses, or I'll put it like that, comma, S. And then we're going to have right here minus 1/4, and so on, plus dot dot dot. So this pattern goes on and on, 3/2 ln 2. Now notice what we have here. This we could rearrange it to get exactly series 1. So what we could do is this is literally series 1. I'll just put a 1 here, and if we look at series 1, is going to be a 1, then 1 minus 1/2. That's just this part right here. So we bring this down there, and then now what we have here is the next one's going to be plus 1/3, which is right here. And then in other words, so now the next one's going to be minus 1/4. Which is just here, and the next one's going to be plus 1/5, which is this right here, and likewise we're going to have a minus 1/6, which is going to be somewhere over there, and then plus 1/7, which is right here, and then minus dot dot dot. This equals to ln 2 though. So in other words, we have the exact same series, but rearranged such that this one we have a plus plus, then minus, plus plus, then minus. And doing that, we get a 3/2 ln 2. But this one's ln 2. So now we get, these are not the same. So this, so I'll put this and this are not equal. So that's fascinating stuff. So not equal. Now that is a question mark. How is this possible? So notice that the above series right here contains the terms as in series 1, but rearranged so that one negative term occurs after each pair of positive terms. So we got 2 positives, 1 negative, 2 positives, 1 negative, as opposed to this one, which is alternating positive, negative, positive, negative. So all we're doing is just rearranging it that way, and we get a different sum. So the sums of these series, however, are different. In fact, Riemann, the famous mathematician that shows up in all of my videos, proved that the summation an is so if the summation an is a conditionally convergent series, so not absolutely convergent, and R is any real number whatsoever, so it doesn't matter what it is, then there is a rearrangement of summation an that has a sum equal to R. In other words, you could rearrange a conditionally convergent series such that so if it's not absolutely convergent, if you take the absolute value and it's not convergent, in other words, it's divergent that way. But if you have some negatives in there, you could make it any value you want. So you can make a conditionally convergent series any value you want, which is absolutely fascinating stuff right here. So yeah, also proof of this is outlined in exercise 4, and I'll go through that very, very soon. Well, not that soon, because these examples are pretty epic. Alright, so now let's look at the exercises, and let's look at exercise 1. And this one, I briefly mentioned this one that earlier in my video when I was discussing estimating sums for the ratio test. So here, remember, I was mentioned estimating sums, so note on there, and then in my earlier videos I would use, I went over various methods for estimating the sum of the series, and those depended on which test was used to prove convergence. And here I stated there are 2 possibilities when we're dealing with the ratio test. We could, if it's alternating, we could just use the methods in my earlier video on alternating series. But if the terms are all positive, then we could use the special methods explained in exercise 1 later in this video. So let's just jump right into exercise 1. So exercise 1, let the summation an be a series with positive terms, and let Rn, R standing for ratio, for the ratio test, Rn equals to an plus 1 divided by a. Divided by an. Suppose that the limit as n approaches infinity of Rn equals to L and is less than 1, so the summation of an converges by the ratio test. And here it's they're all positive, so we don't need to have the absolute value sign there. And here, just to recall the ratio test, let's just scroll up to the ratio test right here. Okay, so this should be somewhere above here. Yes, so we have it here. Actually, scroll up even more. That was the proof of it. So it's right over here. So the ratio test, if we have limit as n approaches infinity of an plus 1 over an, if this equals L and is less than 1, then the series an is absolutely convergent, and therefore convergent in general. And then if it's equal to L and greater than 1, then then it's divergent if it's greater than 1, or infinity. Like that, and if it equals to 1, it's inconclusive. So let's say it converges by the ratio test. So the ratio equals a limit, or it approaches a limit, and it's less than 1. So let's say we have that here. So we have it converging by the ratio test because its limit as Rn as n approaches infinity equals L less than 1. So then this series an inside this ratio is convergent as well. So as usual, we let the remainder capital Rn be the remainder after n terms. That is, Rn equals to an plus 1 plus an plus 2, and then plus an plus 3 plus ... So again, if you recall my earlier videos, I would on the estimating sums. This is after the summation. So let's say we have a partial sum up to Sn. So these are all the terms after that we didn't account in our partial sum, and hence the remainder. So these are what remains. Because remember, we're dealing infinite sums. This can go infinite. Infinite series. This can go infinite. So if the sequence Rn is a decreasing sequence, and we know that Rn plus 1 is less than 1, or actually we're given this one here, because remember the limit approaches L and it's less than 1, but it doesn't say if this is greater than or during it. So let's just say we have Rn plus 1 is less than 1. And we have the sequence Rn is decreasing, so then it says show by summing a geometric series that we have the remainder Rn is less than or equal to an plus 1 over 1 minus Rn plus 1. And remember, this is just a summation of a geometric series. And then B is if Rn is an increasing sequence, show that we have this scenario, the remainder Rn is less than or equal to an plus 1, 1 minus the limit L. Yes, as opposed to Rn. As opposed to Rn plus 1 like that. So that's very interesting. So let's go ahead and solve the solution. Yeah, so what we have is the remainder is, and I'll just write this for completeness, write the whole sequence, or the whole series. So let's say we have n equals to 1 up to infinity. Write this better. And this is a n. Yeah, so what we have is we're going to have a1 plus a2, and this goes all the way, dot, dot, dot. I'm going to go all the way to an here, and then up to an we can consider, let's say if we were able to solve this value, numerically this would be the partial sum Sn. So this is a partial sum equals partial sum, so then the remainder is going to be whatever is after it, partial sum. So then we're going to have the remainder, it's going to be an plus 1 plus an plus 2 plus dot, dot, dot. So now everything opposite of this is going to be the remainder, Rn. Yes, remainder Rn after taking a partial sum Sn like that. So yes, I just wanted to recap on that to make it more clear. So now what we have is, so thus, let's just write down the Rn. So the remainder Rn is, and then we just have that, just write it out. So with a bit more terms. So an plus 1 plus an plus 2 plus an plus 3. And then this can go, let's do one more, an plus 4 plus dot, dot, dot. So now what I'll do is, this is actually a very ingenious method my calculus book does to try to get it as a geometric series there. So what we could do is, well, notice one thing that's always there is if we take out the, well actually, and not that it's always there, but we could try to write it as a ratio. So we know what the Rn is. Rn equals an plus 1 over an, and then the limit is equal to L, which is less than 1. So what we could do here is, I'm going to factor out an an plus 1 from everything. So I'm going to factor this out, an plus 1. So then what we're going to have is a 1 plus, and factoring out on this one, we're going to have an an plus 2 over an an plus 1. Because remember, if you multiply this out, we'll have an plus 1, then we'll have the an plus 1 canceled, we'll just have an plus 2, which is this. So we're not changing anything, we're just changing how it looks, but not the actual values. And then likewise, taking this one out of this one, it's not there, so we could divide it an plus 3 over an plus 1. And then likewise, for the fourth one, we're going to have an an plus 4 over an an plus 1 plus dot, 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 and then put this giant bracket because it goes all the way up to infinity. Yeah, so now one thing we can notice is, well, we have this is an plus 2 over an, that's just going to be Rn plus 1. So this right here equals to Rn plus 1. That's just Rn plus 1. That's just the ratio Rn plus 1, so that we'll have an plus 2 divided by an plus 1. Just as we have here Rn, we have an at the bottom, an plus 1 over there. So now we're going to have Rn plus 1. So now what we could do is even go further, and this is going to be very fascinating. So what we'll do is bring it down. This equals 2, so we keep this factored out, an plus 1 over, and now what I'm going to do is, factor out like this. Now I'm going to do is, on this side here, we're just going to leave it as is, so that this is going to be an plus 2. I'll just write this out as Rn right here. Rn plus 1. And then what we have over on this side, we're going to have here an plus 3. And now what I'll do is what I'll do here is I'm going to multiply, so we have an plus 3, then I'm going to move this over to this side. Yeah, if you can already picture what I'm going to do. I'm going to move this an plus 1 on this over here, just so we're not changing anything. So that's an plus 1, just rearrange it like this. But then what I'm going to do is I'm going to multiply the top and bottom by, you guessed it, an plus 2. an plus 2, so that nothing changes here. This would cancel out with this one. This is just an plus 2 divided by an plus 2, which is 1. So then what we have here at this point right here, this is going to be Rn plus 2. And then this one here, we already know that, that's just Rn plus 1, like that. And likewise, for this one here, for this right here, we're going to write this as an plus 4, and you guessed it, we're going to have on the bottom an plus 3, and then times it by an plus 3 over here, an plus 3, so that those would cancel, so I'm not changing anything. But then this becomes Rn plus 3, like that. And then here we're going to have a An, again, we're going to do the same thing, An plus 2. And then here we're going to have a An plus 2, and then the bottom is just our An plus 1 there. So then these ones always cancel, so they're not changing anything. So this right here is going to be Rn plus 2, and here we're going to have Rn plus 1. And then this keeps the same exact pattern, keeps going on and on. I'll put it like this, dot plus dot dot dot, and then put a giant bracket like that. Yeah, so thus this equals 2, let's just write this all out, An plus 1, then we're going to have a 1 plus, and then, so 1 plus Rn plus 1 times it, plus Rn plus 2 times it by Rn plus 1, and then we have a, over here, Rn plus 3 times it by Rn plus 2 times it by Rn plus 1, and then plus dot dot dot, and this keeps going on and on. And now what I'll do is I'm going to write this, just write this as Rn. I'm going to stay here. I'm going to keep it here because we're going to use this for part B. I'm going to write this equation as, this is going to be, and I'll call this equation, let's write it here, equation 1. Like that. So we'll just call this equation 1 for the uses of this problem. Yeah, so going further, since the sequence Rn right here the remainder Rn is decreasing. Actually, no, I got that wrong. Not capital R. So since Rn, the ratio here, the lowercase one here, we're given in part A, if Rn is a decreasing sequence, and we have Rn plus 1 is less than 1. What we have over here is, we can write this down as the remainder Rn is equal to An plus 1, then times it by, I'm going to write this out, same thing here, Rn, 1 plus Rn plus 1. But then here, here where it gets interesting, so this plus, I'm going to actually remove, not make it equal, I'm going to make this less than or equal to. So now instead of using this original Rn plus 1 times Rn, this is going to be, well, because it's decreasing, so then this is going to be less than if we were to add up instead Rn plus, plus 1 squared. So this is a plus 1 right there. Yeah, in other words here, so it's less than this. I'm going to keep going on and on, but I'll show you what I mean. So in this case here, Rn plus 1 all squared, this is greater than, or for example, I dot E, for example, Rn squared, n plus 1 is going to be greater than, or make it in line with this over here. We could write this as Rn plus 2 times it by Rn plus 1, which is over here. This is going to be less than or equal to just Rn plus 1 squared, because Rn plus 1 is bigger than Rn plus 2. So yes, so this is going to be Rn plus 1 times Rn plus 1, which is Rn squared. And then keep going on and on. We're going to see this exact same pattern. So we're going to have Rn plus 1 cubed right here, where this right here, is going to be greater than this right here. So then, in other words, the remainder here is going to be less than this remainder. So then keep going on and on. So notice what we have. We have a geometric series. Yes, so since Rn plus 1 is less than 1, thus we have that Rn, a capital Rn, is less than a convergent geometric series. And we can scroll up to a geometric series. Yeah, so here I scroll all the way up earlier in this video. So remember the geometric series right here, summation from n equals 1 to infinity of Arn minus 1 equals a plus ar squared, and so on. It's convergent if the absolute value of r is less than 1. And so ours, we're given that Rn plus 1 is less than 1. And then the summation is going to be over here, a over 1 minus r. And if it's greater than or equal to 1, the geometric series divergent. So we're given that Rn plus 1 is less than 1. So what we're going to have is a, let's scroll all the way down here. So that's what we have since Rn plus 1 is less than 1. Thus we have that Rn, the remainder, capital Rn, is less than a convergent geometric series. In other words, right here, we're going to have Rn, the remainder is going to be less than or equal to, and this one here is just a geometric series where the summation is like this, n equals to 1 up to infinity where our a is going to be our an plus 1. And yeah, instead of writing n, I'm going to write k here. So where k, just use different variable. So we have an plus 1 is our a. Yes, so that is our a. And then we have to have r to the power of n minus 1. So in other words, we're going to have rn plus 1 to the k minus 1. So yes, there it is. So when we have k is equal to 1, we have, this is going to be r to the power of 0, which is equal to 1. And when k is equal to 2, we're going to have rn plus 1 over there. And this is going to be our rn minus 1, for example. So I'll just erase that. So that's a geometric series, and we know that this is a convergent geometric series. The rn plus 1 is less than 1. Thus, the summation is going to be, as I showed in my earlier video, a over 1 minus r. But in this case, we're going to have an plus 1. That's our a over 1 minus rn plus 1. And there is the proof. So yes, absolutely fascinating stuff. Alright, so now let's look at part B of this exercise. Scroll up here. So if the sequence Rn is an increasing sequence, show that Rn is less than or equal to an plus 1 divided by 1 minus L. So only difference is this one's decreasing, and we have it such that it's like this. Yeah, so this one, the a was decreasing, and we assumed, yeah, Rn plus 1 is less than 1. In other words, we were taking the partial sum up to a point where it's less than 1 at least. Or a partial sum up to a number such that the next remainder after is going to be less than 1, and so on, just decreases. But if it's an increasing sequence, and then, yes, show that it's basically the same thing, but instead of Rn plus 1, we have 1 minus L there. So let's jump right into the proof. Alright, so note that since the sequence Rn is increasing, and given that, and also given this part right here, this limit as n approaches infinity of Rn equals to L, and it's less than 1. So let's write that down. So given this fact, limit as n approaches infinity, yeah, the limit right here, Rn, this equals to L, and it's less than 1. So we have an increasing, and it's and the limit is less than 1. That means that Rn itself is going to be less than 1. Yeah, so thus what we have is, thus Rn itself is going to be less than L for all n. And then you can see this visually. Basically, if it's an increasing function, let's say we have something that looks like this. Yeah, so we have an xy axis right here, or the n and Rn axis instead, just like that. So Rn, so basically it's increasing, and the limit is going to be less than, yeah, it's equal to L, which is less than 1. So in other words, if we have the number 1 like this, so this is 1, and then we have the number L like this one's L. And yeah, just write that in red. And we have here Rn is, yeah, it's approaching L, but it's also increasing. So that's the key point here. So in other words, yeah, the value of Rn is going to be increasing and increasing and so on. So every single one of these, yeah, these Rn is going to be less than, so this is 1, this is 2, and so on. And yeah, and so on and so on. So this is always going to be, Rn is always going to be less than this L, because the limit is approaching it and it's increasing function. Yeah, so it's always going to be less than L. Alright, so now next step is, well, starting with equation 1 from part A we have, and recall that in this derivation, this is exactly the same thing as for part A and part B, the initial part at least. It's the same thing, we just set it up like this. So we have the remainder, Rn is going to be up to this point, then we just factor out the an plus 1, and then we get something that looks like this, which is, we're going to have an plus 1 plus Rn plus 1, and these ones just do this some algebra, multiply the top and bottom of the same thing, keep doing this, and we get this equation 1. So we'll just start off from here, because it's the same thing. So equation 1, Rn equals an plus 1, and then times 1 plus Rn plus 1 plus Rn plus 2 times Rn plus 1, then plus Rn plus 3 times Rn plus 2, and so on. And let's just write this down. So let's start off with that, because it's the same procedure. So Rn equals to an plus 1 times it by 1 plus, 1 plus Rn plus 1. Let's just see if I get that right. Yeah, so Rn plus 1, then plus, yeah, so an, then we have Rn plus 1, and then plus Rn plus 2 times Rn plus 1, and then plus Rn plus 3 times Rn plus 2 times Rn plus 1, and this keeps going on and on, plus dot dot dot, and this is, keeps going on and on. And now where we know that Rn is going to be less than L for all n, and this is the important part right here. I'll circle this right here. So it's Rn is less than it. So in other words, Rn plus 1 is going to be less than L. So this is going to be less than or equal to L. Actually, we don't need to write that. It's going to be less than L, not less than or equal. So it's less than L, and then this part right here is also going to be less than L. This is going to be less than L. So in other words, the combination of this right here, these two, is going to be less than L squared. And then likewise here is going to be the same thing. We're going to have these, all these are going to be less than L individually. So then the combination of the multiplication is going to be less than, well, all of them multiplied by, L cubed. L times L times L. So this is going to be less than L cubed. Like that. So what we end up having is, well, Rn is, this is going to be now, so if Rn equals that, Rn is going to be less than or equal to, just put equal to sign in case there's some sort of extra case I didn't account for if there's if they're equal 1 or whatnot. But anyways, or an plus 1 equals 0 or something like that. I haven't considered that. But anyways, let's put this less than or equal to, and then we're going to have an plus 1, because either case will work, less than or less than equal to. And then here, 1 plus, this is going to be L, plus L squared, plus L cubed, plus dot dot dot. In other words, we have a geometric series. And since L is less than 1, that's what we were given, then we have that the remainder, again, is less than a geometric series. And remember, the geometric series here, this one initially we had Rn, Rn plus 1 as R there, but now we're going to have it as L. And then this is going to be An plus 1 divided by 1 minus L. So, let's write this down. So Rn is going to be less than or equal to a geometric series, where n equals 1 up to infinity, and this is going to be An plus 1. And then L, right now, instead of n, let's write k, because we have n taken there. So k equals 1, this will be k minus 1, it's geometric series. When you plug in 1 here, we'll get L to the 0, which is 1. And we plug in 2, we have L to the 1, which is 1 there, and so on. This is going to equal to, this is going to be equal to An plus 1 over 1 minus of the R, which is L. Like that. So yes, there's the proof, which is quite fascinating. And so if we were estimating sums and the ratio test works and then all positive terms, we could use these two approximations. So then we can determine what the remainder is. So then the accuracy is going to be accurate up to this remainder right here, this or the other one, or this remainder right here. So it's just quite fascinating stuff. Alright, so now let's look at exercise 2, and this one's going over the proof of the root test. So here we're asked to prove the root test, and hint for part I of the root test, take any number R such that L is such that R is between L and 1, or in other words, L is less than R, which is less than 1, and use the fact that there is an integer n such that, and we have the typical limit formation right here, or limit formulation. So we have the nth root of the absolute value of an is less than r whenever n is greater than or equal to n. So that's a hint that the calculus book gives. And so let's just jump right in and try to make sense of all this. So first of all, recall the root test from earlier in this video, and here I just screenshot from a calculus book. It is more compact. So we have here the root test. So if the limit, so for part I, let's look at part I. So if the limit as n approaches infinity of the nth root of absolute value of an is equal to L and it's less than 1, then the series an, or the summation from n equals 1 to infinity of an, is absolutely convergent and therefore convergent in general. Yes, and the hint now gives, because we know that this root test, so if if the limit equals to L and is less than 1, basically saying take a number R that's greater than L, but it's less than 1. So in other words, in other words, we're just taking a number bigger than L, and we're going to show that using comparison tests later that finding a convergent series with that R means that the one smaller of it will also be convergent. Yeah, so basically what it means, so we're just picking an R between L and 1, so there's always going to be a scenario where that this ratio is going to be less than R whenever n is greater than or equal to a specific integer capital N here. Because all we're doing, all that matters when we're with infinite series is we're dealing with what happens as you get larger, as n gets larger and larger. So eventually there's going to be a scenario such as this right here. And that is because, again, we're given that L is less than, so the root test here, L is less than 1. And we're picking a number R between, L and 1. So this will make more sense as we go through this proof. So following the hint, we get that. So let's just write this down. So we have absolute value, the nth root of the absolute value of an, so that's this part right here, is less than R. So in other words, what we could do here is, we could rewrite this as, so I'll just write this as, like here, this is going to be whenever, I'll just write this here. So whenever n is greater than or equal to capital N. So then this one right here, we could rearrange it such that just take this to the power of n. So we could just take this to the power of n like that, and this to the power of n. So what we end up having is, I'll just write it like this. So I'll just write it like this for completeness. So we could have, this is the same thing as writing an absolute value of an like this to the power of 1 over n less than R, like that. So then, now we could just take it to the power of n. So we'll just take this to the power of n, and this to the power of n. So then what we end up having is, this just cancels, so we're going to have absolute value of an is less than Rn, and then we have it a bit easier way to understand this one, a bit more comprehensible. Dealing with roots is not that straightforward. So whenever n is greater than or equal to capital N. And I'll just circle this right here, or square it. So we have this right here. Alright, so now since L is greater than or equal to 0, that is, it's the absolute value here, we're taking the limit is of an absolute value, the nth root of an absolute value, so it's always going to be greater than or equal to 0. Can't have a negative there. And it's also less than 1, and we're given, and we chose R such that it's greater than L and less than 1. We have, R is going to be, R is positive and less than 1. So R is greater than 0, because it's greater than L, like that. So if L is 0, then R is greater than 0. And thus the following geometric series converges. Remember, the geometric series is if the R is equal to, it's less than 1, then it's convergent. In other words, right here, this Rn is a convergent series. So we could take the summation right here up to infinity from n equals 1, and this is going to be Rn. This is just a geometric series. This one, you could write this as like this, n equals to 1 up to infinity, and just factor out an R just to make it look exactly the same format. R to power of 1, R to power of 1 is going to be times it by R to power of n minus 1. So this is the geometric series where that is our A, this is our R. So And here I quickly teleported to the geometric series recall in my from my earlier video earlier in this video, just because it's this video is pretty long, so I want to refresh it again and again. So we have here geometric series AR n minus 1 from n equals 1 to infinity. The summation is convergent if absolute value of R is less than 1, and its sum is here. We have A over 1 minus R. So let's just teleport back again. All right here. So we just teleported back over here. So that so that is a convergent geometric series. So so in other words, we have every term an, absolute value of an is less than a convergent series. So in other words, or less than the terms of a convergent series. Otherwise, we could just use comparison test. So let's just keep going here, and so and since the absolute value of an is less than Rn4, again we chose the n is greater than capital N. By the comparison test, we have that the summation up to infinity of from n equals to capital N. So we're starting from there because that's what we were given. That's what we initially specified as R is based on this capital N there. And then this is the absolute value of an converges as well by the comparison test. Because every term, absolute value of an is less than Rn, converges. And since we don't care about a finite number of terms, from n equals 1 to up to n minus 1, that's also going to be convergent. Yeah, and since convergence does not depend on a finite number of terms, we have that the summation up to infinity from n equals to 1 of absolute value of an, this also converges right here. So in other words, this is absolutely convergent. Yeah, so and thus, so that converges, that means that just a general general series an, the general series absolute value from n equals, the summation from n equals 1 to infinity of an without the absolute value terms is absolutely, yes, so I was right, absolutely converges. Yeah, so remember, if it converges, if it absolutely converges, means the absolute value of it converges as well. So hence, this converges as well, and converges, absolutely converges, and converges, and therefore convergent, and so on. But I'll just leave that because that's just same thing. All right, so now let's look at the second part of the root test, part II. So let's just go review it here. So if limit as n approaches infinity of the nth root of an, or absolute value of an, equals to L and is greater than 1, or we have limit as, the limit equals to infinity, then the series, but in either case, these are all both greater than 1, because we're dealing absolute values, so all is positive. Then the series right here, summation an is divergent. Alright, so let's get to the proof. So since we have limit as n approaches infinity of the nth root of the absolute value of an is going to be greater, it equals to L, and is greater than 1, or actually better yet, because to combine both of them, so remember this one is greater than 1, equals L greater than 1, or it goes to infinity, I'll say both of these are greater than 1. So since we have, so we have this for both scenarios, of part II, then there's an integer capital N such that, and again very similar to the part I proof, such that we're going to have nth root of absolute value of an is going to be greater than 1 whenever, calculus book says for all n is greater than or equal to capital N. And the reason here, because this one is the limit as n approaches infinity. So this one's approaching infinity, so at some point we're going to have specifically capital N, where n greater than that is always going to be the nth root of it is going to be nth root of the absolute value of an is going to be greater than 1. So yes, when we're dealing with infinite, with limits, or as n approaches infinity, so anything with infinite, anything with approaching infinity, the number of terms. So we always need to write it like this. Usually write it like this in the precise definition of limits formulation, as I've gone over my earlier videos, just to get specific values here, or specific terminology. So we have this scenario. Now we're going to do rearranges as well as before. This one, take the take the power of n on both sides, so that this cancels out. So what we're going to get is a absolute value of an is going to be greater than 1 to the nth, which is just 1, because 1 to the power of anything is going to be 1 for all n. For all n, for all n greater than the specific value, capital N. There. So in other words, that's what we have is the limit. Because remember the test for divergence, the limit as n approaches infinity of an in general, without even the absolute values, because even if it's negative, it's still not going to equal 0. So then an right here, because the absolute value is greater than 1, an is not equal to 0. So we have, so let's write it like this. Let's write it like this. Summation, right, better. Summation from n equals to 1 up to infinity of just generally an diverges. So let's write diverges, and this is by the test for diverges by, and I'll just write this all out, by the test for divergence. So yes, fascinating stuff here. So let's circle this right here. Yeah, here actually I just boxed this out better like this. Yeah, so again, test for divergence, if it's not equal to 0, so in other words, this an, yeah, when we're dealing with infinity, you're going to keep constantly adding terms that are not, the limit is not approaching 0. So you're adding terms that are of decent sized, and terms that are getting further and further, or that are not equal to 0. Or that are not approaching 0. So you're always going to be increasing the value, and you're going to go, yeah, it's going to be going to infinity. So especially here where it's greater than 1. All right, so now let's look at the part III, or triple I, or part 3. And this one here says, if limit as n approaches infinity of the nth root of absolute value of an equals to 1, the root test is inconclusive. And here, so the solutions manual, the way it does it is it considers the following two series: the divergent harmonic P series, yeah, where P equals to 1. Recall, yeah, if P equals to 1, or yeah, P is, yeah, here I quickly teleport this, yeah, so if P is less than or equal to 1, here's divergent, and this is the 1 over NP. Is convergent if P is greater than 1. Just recap. And let's just scroll down a bit more. Here's the comparison test. And yeah, this one here is I used it earlier just now. I just wanted to recap quickly. So yeah, if an, the terms are less than bn, which is bn is a convergent series, then this is also convergent, and vice versa. If these terms are greater than a divergent series of terms, then it's divergent. And also, I believe there's one more to double check. There's geometric series. And yeah, the test for divergence. So if the limit an does not exist, or if this limit approaches is not equal to 0, then the series an as n approaches infinity from up to, yeah, as n approaches 1, n equals 1 to infinity, the summation an is divergent. So this series is divergent, and there's the link to it. And it was a scroll down. All right, so let's consider the divergent harmonic P series, where just P equals to 1, as I've gone over several times, and prove that it is divergent in earlier videos. So and the summation up to infinity from n equals to 1 of 1 over n. Yeah, so if we were to take the root test of this one here, so we'll take the nth root, so we'll have the nth root of the absolute value of an, in this case it's going to be 1 over n. This equals to the nth root of 1 over n. So remember, this just equals to 1 over n to the power of 1 over n. So now, interesting here, taking a limit of this is going to be a very interesting derivation for just this limit alone. So limit as n approaches infinity of 1 over n. And here it's absolute value, but it's all these are positive. There's no way of getting negative, so yes, get rid of the absolute value sign. Just leave it 1 over n. And so we're going to have 1 over n like this. So now we have an interesting scenario. How are we going to solve this one? And also, yeah, before I derive it or solve it, I'm going to simplify this even further. Let's just go make this n to the power of negative 1 over n. This is the same thing. So you just move it up and put a negative, and we have this right there. And just write this one right here. N to the power of negative 1 over n. So now this equals to question mark. How are you going to solve this one? Because we have a scenario of a infinity to the power of 1 over infinity. So yeah, it looks like we could use L'Hopital's rule, or we should be using L'Hopital's rule, but it's not directly applicable right now. So I was scavenging actually all online, because my calculus book didn't explain how to derive it. It just said that the limit is equal to 1 for some reason. So, but I found a derivation of it. So the way to do this one here, so basically, move this all over there. So if this limit exists, then we have, in here, just quickly rearrange this. This is better, it looks better this way. So infinity to the power of negative 1 over infinity equals question mark. So yeah, so if this limit exists, then what we end up having is limit as n approaches infinity of n to the power of n to the power of negative 1 over n equals to a. Let's say, so the limit exists, it equals to a. Yeah, so now what we could do is, well, ln both sides. So, yeah, I'll ln both sides and move this over to this side. So we're going to have ln a, so move it here. So that's what you're going to have. ln of a equals 2, and then we ln of this whole limit. And remember, we can just move the limit inside and outside the functions, as I illustrated earlier by that composite limit theorem, limit of composite functions theorem, and so on. So with limits, we could just take this out. So this is going to be equal to I'll write for completeness. Ln of limit n approaches infinity of n to the power of n to the power of 1 over n, like that. This just equals to limit as n approaches infinity of ln n to the power of negative 1 over n. And if we recall the ln rules or logarithmic rules, this can go down, so that power goes down. So this equals to the limit as n approaches infinity. You have n approaches infinity, and then now we're going to have a negative, negative 1 over n times it by ln n, like that. So that's what we have. Put this bracket. Alright, so now what this equals to, we can simplify this even further, move the negative out of there. So negative limit as n approaches infinity, and then we're going to have a ln n over n, like that. So in other words, what we're going to have here is, let's move this, get the n's out of there. So ln n over n. This right here approaches, ln n approaches infinity as n approaches infinity. So we're going to have infinity over n, which is also approaching infinity. So in other words, this is undefined, but we could use L'Hopital's rule. And here, recall from my earlier video on L'Hopital's rule. So for these scenarios, we can apply. So recall L'Hopital, I believe it's, so my calculus book spells it as L'Hospital's rule, but you pronounce it without the S, and some people write it without the S as well. But this is what I've been growing up using. So recall L'Hopital's rule, and we're gonna write limit as limit as n approaches infinity of, if we have a function like this, f of x over g of x, where they're approaching infinity, or another scenario like a 0 over 0. So this equals to the we could take the this equals to the limit of the derivatives. So this is going to be f prime of x over g prime of x. So let's just circle this right here. Yeah, so thus what we have is thus we have ln a equals to equals to the negative times it by the limit as n approaches infinity of the derivative of ln n. So I'll write d over dn ln n over d over dn of n. So in other words, remember recall the derivative of ln n is just going to be 1 over n. So we're going to have limit as n approaches, there's going to be a negative sign there too. So negative limit as n approaches infinity of 1 over n divided by, well, that's 1. The derivative of n is just 1. So in other words, we just get a scenario where this is negative limit as n approaches infinity of 1 over n. And now here, this is going to be 1 over infinity. So in other words, this is going to be approaching 0. So this equals to 0, and negative times 0 is just 0. So this equals to 0. So box this out. So thus what we have is ln a equals to 0. In other words, by definition, and you can also rearrange this, by taking the power of e on both sides, so e like that. So I'll just put it in lighter, so we can take the e and e like that. So you could write that, or then the ln's cancel, or a equals to e to 0. E0, which equals to 1, and again, this is by definition. And this is, I'll put bracket by definition of power rules, like that. Yeah, so thus the ratio right here, thus the root test gives it 1. Move this over. So thus we have, let's put this all in fully like this. So thus we got the limit as n approaches infinity of the nth root of an, in this case equals to 1, where an is equal to, it's 1 over n. I'll put that like this: absolute value of 1 over n is just 1 over n, and so on. Let's just keep an there for this scenario. So we have it equals to 1 for this divergent harmonic series. So now let's look at another series. So now similarly for the convergent P series, where if P equals 2, then we have a convergent series. So similarly we could do the same thing, and I'll show that this also equals to, the root test also gives 1, but it's convergent in this case. So n equals 1 up to infinity of 1 over n squared, where P equals to 2 there. So what we have here, we take the limit as n approaches infinity of the nth root of the absolute value of an, and this one is n squared, and n is always positive, so this is always going to be positive. We don't need to include the the absolute value sign. So this equals to limit as n approaches infinity, and what I'm going to write this as, like here, this is equal to, so an is going to be 1 over n squared. So 1 over n squared, and then just take this out like that, write it in this notation, to the power of 1 over n. And now this one right here, going further, this equals to, this one we could even simplify this even further. This equals to the, you do the same thing as before, so move this over to the top. So we're going to have it equal to limit as n approaches infinity of n to the negative 2 over n. And we could also separate this even further and use the answer from the previous derivation over here, it equals to 1 there. So we can go like this, limit as n approaches infinity of, and I'm going to write this as n to the power of negative 1 over n times n to the power of negative 1, like that. So in other words, this combines, you should add the powers, you get n negative n to the power of negative 2 over n is the same thing as that. And this one we can just separate this using limit laws. So this is going to equal to limit as n approaches infinity of here is going to be n to the power of negative 1 over n times by limit as n approaches infinity of n to the power of negative 1 over n. And this one here is exactly the same thing we just solved over this one here. This is the same thing, n to the negative 1 over n, like that. It's the same thing as this one right here. So in other words, this equals to 1. So this equals to 1, this equals to 1. So this just equals to 1 times 1 equals to 1. Equals 1 times 1. And just let's write this equals to 1. For completeness, right, it's thicker. So this equals to 1 times 1, which equals to just 1, which is the same as before. So in other words, we have for both of the series, one's convergent, one's divergent, and they both equal to 1. So then, so a divergent harmonic, P series 1, and a convergent P series of P equals 2, and the root test gives 1. So for each sum, we have the limit as n approaches infinity of the nth root of absolute value of an equals to 1. And here I'm just going to scroll up here, so this is for, just write this here to make it different from that. So the absolute value of 1 over n, like that, is going to be equal to, it's equal to 1. So what we have is, so the root test doesn't give us anything when it equals to 1. The root test is inconclusive when we have this scenario when the root test gives the answer 1, when the limit as n approaches infinity of the nth root of absolute value of an. So as those two shows, you take two series, and if you find one contradiction, that usually means everything is inconclusive. So going further, so exercise 3. This one's a very interesting exercise right here. So given any series of in any series, the summation an, we define a series like this, a plus n, the summation of that, whose terms are all the positive terms of this the series an, and then we also define a series with this a to power of a minus n, like that. I mean an with a minus sign on top. This was an with a plus sign. Those are all positive terms. And then this one is all the negative terms of the series an. So to be specific, we let, this is a very ingenious method actually my calculus book does. So an with a plus equals to an plus the absolute value of an divided by 2. And then for the negative terms, we have an minus equals to an minus absolute value of an divided by 2. So notice that if an is greater than 0, so then what we'll have is we'll have an plus equals to an, because otherwise we'll have an plus an divided by 2. That's just going to be an. Whereas if an is less than 0, actually no, before I get to that, so we have an is greater than 0, and on this case, if an is greater than 0, we're going to have an minus an, so then an minus is equals to 0. Whereas if an is less than 0, then what we are going to have is, what we have is an minus, right here, we're going to have an minus absolute value of an, which is, well, 2 negative. So we're going to have an, which is negative. This one's going to be minus this one. So then that's going to be, and then divided by 2. So that's going to equal just to an, which is going to be negative. And this one, an plus, will equal to 0. So in other words, here we're going to have, this one's going to be negative, plus absolute value of this one can be positive, so we're going to have this cancels, it can be equals 0. So an plus equals 0. So it's absolutely, yeah, it's pretty ingenious when you think about it. It's pretty amazing. So let's look at part A states, if the series an is absolutely convergent, show that both of the series an plus and an minus are convergent. So both of the positive and negative terms, if you separate those out, are convergent. And if an is, the series an is conditionally convergent, show that both of the series an plus and an minus are divergent. So remember, conditionally convergent is where the absolute values of the terms are not convergent. And this one absolutely is that the absolute values is convergent, and hence it's also convergent generally as well, like that. So let's look at the solution. So solution, since the absolute value of, since the series an, or the summation an, is absolutely convergent, and since what we have is an plus is going to be less than or equal to an, the absolute value of an, and what we have is an, because remember, this an plus can either be an an or a 0. That's it. So it's going to be less than or equal to this. And an minus is also less than or equal to the absolute value of an, like that, because again, it can either equal to an or equal to 0. So remember, this can equal either an or equals to 0. And this one can equal to an or equals to 0, depending on if the an is positive or negative. And I'll just write this out even in more detail. So because an plus this equals 2, so this equals to, well, an, this is a positive term if so if an is greater than 0. But if an is less than 0, equals to 0. So if an is negative, like that. So it can either equal, so it's going to be less than or equal to, it's either an or 0. The absolute value of it's going to be less than or equal to that. And we have an minus equals to, so if, so it equals to an at the bottom here if an is less than 0. So if it's less than 0, we're going to have a negative here minus a negative, minus absolute value term. So we're going to have a negative minus a term. It's going to be, again, then divided by 2, it's going to be an. And equals to 0 if an is greater than 0. So if it's greater than 0, we're going to have subtract the cancel out. So yes, fascinating stuff. Yeah, so we thus conclude by the comparison test that both an plus and an minus must be absolutely convergent. In other words, we have right here the an is absolutely convergent. So this the series of the absolute value of an right here, that is convergent. So then this is going to be convergent as well, absolutely, because it's less than it. Every term is less than a convergent series of terms, and both one here. So every term of this negative terms are going to be less than or equal to the, when we take the absolute values of a convergent series. So yes, or the terms of convergent series, which is the absolute value of an, and hence an as well is going to be convergent because it's absolutely convergent. Yeah, so hence both are convergent. And note we can also solve part A as follows. So what we could do is, well, if we let the absolute value here, just the second way my calculus book mentioned in the solutions manual. So from n equals 1 to infinity of the absolute value of an. So this number, this is a absolutely convergent. So this one is going to be equal to, I'll call this L1. So this is absolutely convergent. Yeah, it means absolute value is equals to L1 is a limit. And so we also have an and. The summation of up to infinity of n equals to 1 of just an by itself. Because remember, if it's absolutely convergent, it's also convergent. So we'll call this L2. So a different one could be different, and it's also convergent and up to limit L2. So thus what we have is, well, the summation up to infinity of n equals to 1. If we look at the positive term, so we have an plus like that. So an, the absolute values of it. And remember, this just equals to, scroll up, an plus the absolute value of an divided by 2. So this equals 2. And now we could just sum this up to infinity, n equals to 1. And now we're going to have an plus, and here actually we don't need this absolute value sign, we just remove that. So this equals to an plus the absolute value of an like that over 2. So in other words, this just equals to, well, this is going to be 1/2 of, this one's going to be L2. This one, now we're going to plus L1 there, like that. And when we're adding, yeah, so basically when we're adding right here, when we're summing up convergent series, this also is convergent by the theorem I mentioned earlier in my video. So this is also convergent. Because all we're doing is subtracting, adding, and then in the negative terms we'll subtract convergent series. So in other words, we're going to get a convergent, so this is going to be convergent. Like that. So this is convergent. So that's convergent, and we'll just box this out. And also, and similarly, just for the other one, summation from up to infinity from n equals 1 of an minus, this just equals to an minus like that. This equals to, this equals to, let's put it like this, n equals to 1 up to infinity, and this one is just an minus absolute value of an over 2. And again, just to double check. So yeah, an minus absolute value of an over 2. And this just equals to, this can be L2, and this is going to be a 1/2 L2 minus L1. And then this is also convergent. And this is, convergent. Because all we're doing is subtracting two convergent series. So in other words, we're going to have a convergent series. Alright, so now let's look at part B of this exercise. This part B says if the summation an or the series an is conditionally convergent, so in other words, the absolute values is not going to be convergent, show that both of the terms, a an plus and an minus series, are both divergent. So let's go and take a look at this. So we will show by contradiction that both an plus series and an minus series must diverge. For suppose that an plus converge. So let's assume it converges. Yeah, so if we suppose that this the series an plus the positive terms converge, then so would the following series, and this is again because we are just adding them. So if we have right here, the summation n equals to 1 up to infinity of right here, I'll just write this an plus, and also minus 1/2, and this will make sense later. So let's put a minus 1/2 right there, like that. So if we sum this up, this just, again, you can just break this up into their parts. So this can be n equals to 1 up to infinity, an plus, and then minus right here, 1/2 of the summation an, like that, n equals to 1 up to infinity. So this one we know is convergent. So this is convergent. This is convergent right here. Because it's we're given that it's conditionally convergent, the an series. Hence, this is convergent. But the absolute, when you take absolute value, it's not convergent. So that's convergent. So then this should be convergent. Yeah. So then I'll write it like this. So if this part right here, if it's convergent, so if an plus series is convergent, if convergent, And then, so if that's convergent, this should be convergent right here. Then I'll put an arrow, should be. It should be convergent. Yeah, so this should be convergent, but if we were to rewrite this in a different way, so but this series right here, so but summation infinity, summation up to infinity n equals 1, we'll have an plus minus 1/2 an. So this equals 2, and we know that an plus, this one is equal to, again, we just defined that it's all the positive terms, so an plus absolute value of an divided by 2. So yes, so that equals 2. Let's just put that inside, so this equals to the summation. So infinity n equals to 1, and then we're going to have like this. We'll put a giant bracket. This is going to be equal to, again, this is why we added the 1/2 there. So 1/2, and then this is going to be an, and then this is going to be plus absolute value of an, like that. And then minus 1 over 2 an. That's this part right there. Close bracket. Yeah, so that's why we added the 1/2. So as you can see, when you multiply 1/2, what happens is this, and yeah, so this cancels with this right here. So what we're left with is, these two cancel. So we're just going to be left with 1/2 an plus. An absolute value of an. So this equals 2 summation infinity n equals to 1. This is going to be 1/2 absolute value of an. And here I just moved the 1/2 out of there, just like that. So this is divergent. So this is because, remember, it's not absolutely convergent. It's only conditionally convergent. In other words, the absolute values of the terms are diverged. So this is divergent. I'll just write diverges like that. Yeah, so in other words, what we have is this, summation, or this subtraction right here, this combination of the two series diverges. But if but if this was convergent, then the combination of the two series should be convergent. So otherwise, this is not convergent. So note that the absolute value, the series of the absolute value of an diverges because the series an is only conditionally convergent and not absolutely convergent. So here's bold this. So yes, so hence the series an plus can't converge. Otherwise, this would be convergent. And again, as I discussed by my earlier theorem, when you're combining the infinite summations. So infinite summations of convergent series. So similarly, neither can the absolute value, neither can the series of the negative terms an minus. And yeah, just for completeness, you could do the exact same thing. So I'll just do it. Yeah, without the n equals 1 to infinity, just write it like this. Calculus book uses this sometimes for just quicker notation. So an minus, not minus 1, just an minus the minus 1/2 an. So if this series like this is convergent, so if this is convergent, we should have something that looks like this. This is going to be the summation an minus 1/2 of the summation an. So I'll just circle this right here. So we have this, and this also equals to, so it equals to that, and then you could also expand this one out. This one's going to be the summation an, put a bracket like this, 1/2 of an minus is going to be just an minus absolute value of an, and then minus right here we're going to have a 1/2 an, close bracket. So what we're going to be left with is, well, this cancels with this. So we're just going to be left with equals 2. Then take out the 1/2 and negative here. It's going to be negative absolute value of an. So negative 1/2 the summation of absolute value of an. And we know that this diverges because it's not conditionally convergent. So this right here diverges. So diverges, so hence this can't converge. So then, thus, because if this converges, this is conditionally convergent, then this should be convergent. Thus, absolute value, thus the series then of the negative terms an minus diverges. Yeah, so diverges because right here, because again this part right here diverges. So because an conditionally converges. Conditionally converges, like that. Alright, so now this brings me to the last exercise in this, again, this epic long video, as is becoming customary in my recent videos. So exercise 4, prove that if the series an is a conditionally convergent series and R is any real number, then there is a rearrangement of the series an whose sum is R. So yes, this is a part of the rearrangement section that I went over briefly earlier in this video. And now we're basically saying if it's conditionally convergent, then R is any real number. So basically you can rearrange to get any real number, to make it sum up to any real number, which is quite fascinating stuff. So hints, part 1 says use the notation of exercise 3, which is looking at the positive and negative terms like this, an plus and an minus. Use that notation for the positive and negative terms. And then 2 says take just enough terms of an plus so that their sum is greater than R. So basically greater than R there. Then add just enough terms an minus so that the cumulative sum is less than R. Continue in this manner and use the following theorem also from my earlier video. So this one here, if the series an is convergent, series an convergent, then the limit as n approaches infinity of an equals to 0. So yes, if it's convergent, then the terms have to be going to 0. And as you can see, what this pretty much shows is that we can just take the positive terms greater than R, then take the negative terms to make them cumulatively the whole sum less than R. So we swing back and forth, but then the terms an are going to 0. So as you're taking larger and larger values, it's going to go 0, 0. So it's going to be pretty straightforward that you can do this. So continue in this matter and use this following theorem. So solution. Let the series Bn be the rearranged series constructed in the hint that we're given here. Pretty straightforward. They pretty much tell the answer, but in just an abstract way. So let's write this rearrangement of an, and we'll call this Bn. N equals to 1 up to infinity. And again, when we're dealing with infinity, we could do a bunch of cool stuff. And this is going to be Bn. This is going to equal to, well, this is going to be, we're going to take the, so the hint, we're going to take just enough terms of a plus so that their sum is greater than R. So let's say we take the summation an plus from n equals to 1 up to n equals to capital N1. And now recall, so if at n equals 1, an plus is going to be negative, this just goes to 0. Remember the notation. So if it's less than, if it's a negative number, it's going to be equal to 0 for this formulation. So we just go all the way up to capital N1, and then we plus. So once this, let's say this is at this point here, this is going to be I'll call this Sn1. The partial sum right here. So this is partial sum Sn1, and I'm not specifying which one it is because this could be, it doesn't necessarily mean up to n1. Actually, since we are actually dealing with, if we're going to have zeros there, so we'll include that in the partial sums. So this will go all the way up to Sn1, so partial sum like that. And this is going to be, let's say it's greater than R, just greater than R. This is going to be partial sum, like that. And then we're going to add, all the negative terms such that, so let's go like here. All the negative terms, so this is up to n, it's also going to be from n1 up to n equals to, I'm going to call this k1. Because remember, if it's positive, it will be 0, and if it's only negative, it will count as a real number then, not 0 number. So this is all the way up to k1, because it could be less than n1, capital N1, greater than n1, and so on. Because we're just taking whatever it takes, such that now the partial sum here, So the partial sum all the way up to here when we add all the negative terms, because remember we're going to add it such that the cumulative sum is less than r. So then now this partial sum here, for when we include this and this, is going to be less than r, just less than it. So SN1 plus K1. So yeah, so we include the zeros, so this is all the way up to the partial sum up to when you add those two. This is going to be less than r. So yeah, so alternates initially up to greater than r, and eventually we're going to have it less than r there. Now we're going to add all of the positive terms again. And then we repeat this process again, continue in this manner, and so on. Yeah, let's just do this one or two more times to see what happens here. So plus, and this is going to go, because we already have the positive terms up to n1 there. I mean capital N1. So we're going to have capital N1 plus 1 up to n equals to n2. Yeah, so just write it like that. Yeah, n2 is moved it down a bit. So this is going to be the positive terms again, an plus. And again, now the cumulative sum of this one all the way up to here. This is going to be s of, this one's going to be, yeah, this is going to be actually, it's interesting. This would be, it took me a while to realize this. I realize it now actually. It's going to be Sn, capital N2 plus the K1 there, the number of terms there. So yes, this gets all the positive terms up to here, and then the also we have to include the negative ones here, so the K1 terms. And then likewise, the next one, let's do one more. Now we add all the negative terms, and this one again, this needs to be greater than r. So the cumulative sum is going to be greater than r. So it's going to be greater than r initially, then less than r, then greater than r, and eventually here we're going to be dealing, because we're dealing with infinity like this. This is going to be n equals 2 k2, because we're doing all the negative terms, an minus, adding them up, and then we're going to start off from, because we already took all the negative terms up to the k1, we're going to go k1 plus 1. So remember, if there's any positive terms in here, it's just going to equal to 0. So it doesn't add anything. So we can even have like 1,000 zeros before we get one that's positive. I mean, one that's negative in this sequence. So because we're dealing with infinite terms. So plus dot dot dot. And likewise, let's write this entire one here. So this one right here is going to be, that is all the way to K2. So that's going to be Sn2 plus K2. So yes, we need to, actually no, yeah, Sn plus, so it needs to add up all of the terms of the positive and all of the negative terms. So, and it goes all the way to K2. So, and this one's going to be less than R. It's the cumulative sum. So yes, fascinating stuff, and it keeps going on and on. Yeah, so note that this series can be constructed this way by virtue of the result from exercise 3b, which states that if the series an is conditionally convergent, then both an plus and an minus are divergent. So remember exercise 3b. So here, which I showed that, yeah, so we will show by contradiction these both diverge. So I'll go scroll up to the exercise question. So if a series an is conditionally convergent, show that both of these, the positive and negative terms of the series, of those separate series are also divergent. Yeah, so the terms, the negative terms diverge and the positive terms diverge. In other words, they get larger and larger. So yes, as I showed, they get larger and larger. So what that means is, hence we can keep adding their terms to obtain as large of a number we want, since there is no limit. So they don't approach a limit. So we could always collect enough of these such that we can have the cumulative sum greater than r initially there, then less than r, then greater than r, then less than r. Even if we have to take 1 million terms, we can do that because they diverge. There's no actual limit. It goes to infinity. So we could do infinite things when we're dealing with when we have an infinite limit then. So this series, so hence we can keep adding their terms to obtain as large of a number we want, since there's no limit. This series Bn, this rearranged of the an, will have partial sums Sn that oscillate in value back and forth across R. So yes, here. So the partial sums here oscillate greater than r, less than r, eventually here. So when we get to capital N plus K1 and so on. Since an, the series an is convergent, we can apply the given theorem from our earlier video, which they put a link here. Yeah, they put a link over here. So the series an is convergent, then the limit of the terms an of the term an is approaching 0 as n approaches infinity. So yes, the terms themselves are approaching 0. So we can apply that theorem right here. So limit as n approaches infinity of an, these terms are approaching 0. So in other words, what this means is if they're approaching 0, here to ensure that this is possible, we need more and more terms to make sure that they oscillate back and forth. So this one is going to be, as this goes to infinity, we're going to eventually have it that this is going to be greater than these terms, greater than this term, and so on. Yeah, so now since we're dealing with infinite divergent series, we can ensure that our construction of the rearrangement of an, we'll call this series Bn, has oscillations, the absolute value of Sn minus r, that are always less than the absolute value of an, that term, the nth term. For example, and again, it's because of the nature of infinite divergent series. So for example, let's say we had the conditionally convergent series an, like that, and from n equals 1 to infinity, and let's just say it had terms such as 1 plus 2 minus 3 minus 4 plus 5, etc., plus 6, and then minus 7 plus dot, just keeps going on and on. But again, we're dealing with infinity, and this is eventually going to go approach 0 there, so it's going to get smaller and smaller. But in any case, so as it goes 0, but we could always choose that it gets smaller. I mean, we could always choose it such that, let's say if we have that, and we have, let's say we have r equals 5. So we just choose r equals 5 as any random number, and then what we have now is the rearrangement Bn from n equals 1 to infinity. We could take all the positive terms until they're greater than 5. So we can go doing my method here. This one is just a generic one. You could do many different methods here. This one would use an plus, so that the negative terms will be a 0. So we'll have here it's going to be 1 plus 2. And this one's going to be a 0. So that goes to a 0 there. And then plus again, it's a 0. Like that. And then here's a 5. So we can have it. So you could do this method. This is going to be 8. So that's going to be 8. And this is going to be greater than 5. So we can always just do this. And then that's going to be greater than 5. That's going to be this is going to be S5 there. And then now for add the negative terms. So we can have, my method would just have, this would be a 0. Like that would be 0. Minus 0, minus 0 again. And then I'll just remove this 5. Only include the zeros. And then this is going to be a 0 as well there. Like that. And then finally we're going to have negative 3. Negative 3. And then, yes, negative 3. And then one more than negative 4. So that it's fully less than it. So then this right here is going to be negative 7. Yeah, so that's negative 7. And then this right here, the combination of these two is going to be 8 minus 7, which is going to be, well, equals to 1. That's less than 5. Now in this scenario right here, so this the difference right here, so this part right here, we have the oscillation Sn minus r. Sn is going to be 8, so that's going to be 8 minus r is 5. Absolute value is going to be equal to 3, like that. So 3 is going to be less than, well, it should be less than, so that's S3. So this is equal to, so it's right here. This is going to be S all the way up to 5. S5 minus R. And this equals to 3. And S5 here is, A5 is 1, 2, 3, 4, 5. This is A5 there. This is A5. This is actually, this is going to be less than A5 here. So the absolute value is less than A5, absolute value. So we can construct it such that that is the case there. So we can always less than it. But here in this case, notice what happens here is this is going to be negative 7 there. So when you subtract, we'll have 1. But then now the difference here, this is going to be our all the way up to, this is 5, 6, 7, 8, 9. So yeah, this is going to be S9. S9 is equal to, yes, absolute value of S9 minus R equals to 1 minus 5, which equals to 4. But then this equals to, in this case, in our case, let's see what the S, actually 1. This is 1, 2, 3, 4, 5, 6, 7 there. This is a 7. Yeah, this is actually, this is still going to be less than a 7. absolute value of A7. So we can construct it like this. If it's greater, we could choose a different one. So this doesn't need to be like this. We could choose a different one. We could replace this by a negative 3 there. Let's say we had a 3 somewhere there. Negative 3 somewhere in the 1,000,000th one there. And so on. It doesn't need you need to follow this. I just put the zeros there just to follow this rigid one if you put in a calculator or a computer spreadsheet, etc. So it could be negative 4 or 3 or anything. So it could be, let's put this in bracket, or negative or use let's say a 7,000,000 or 700. And put that in there where it equals to negative 3, and so on. So again, it does not matter what it is, because we're dealing with infinite terms. We can go deal with whichever one we need. And since this is approaching so basically we can always choose that it's less than this, but this is also approaching 0. So that means that we need more and more terms. Yeah, so thus what we have is as this is approaching infinity, and this is this difference right here. We could always choose it's less than an, the absolute value of an, so thus the limit as n approaches infinity of this difference, Sn minus r, we could choose this to be less than the limit as n approaches infinity of absolute value of an, because again, we can construct it however we want. And this equals to 0, we know that, because absolute value of an is, because the limit of an is approaching 0, so absolute value is also going to be approaching 0. Yeah, so what we have here is this just equals to 0, so what we get is, just move this over to the other side, limit as n approaches infinity. Yeah, the limit as n approaches infinity of Sn there, this equals to, well, just r, because this is approaching 0 there. So it's less than, the absolute value is less than 0, so in other words, it's approaching 0. That's the only way you can go about it. I mean, and not 0, r. I got that mixed up. So this is approaching, so the only way this can be the absolute value less than 0, but it's approaching 0. Same thing as less than or equals 0. This is the absolute value of it, so you're approaching r. So in other words, this right here is the partial sum. So thus, let's put this here. So thus, so thus here. Well, actually, I put the thus here. So thus, the rearrangement of Bn right here, rearrangement of An, which is Bn, from n equals to 1 up to infinity, this just equals to, that's just going to be equal to the partial sum, the limit of the partial sum. Limit as n approaches infinity of Sn is equals to r. Like that. So hence, you can make it whatever we want, like that. And then if you were to graph this out, how this would look like, well, let's say we have a graph like this. And this is n. This is going to be our Sn. So then we have our r is this. Let's draw this better. So there's our r. So we have any number r. What we can do, we can construct as we're dealing with infinity. Let's say call this this n1 there is at a specific number of terms there. And let's say we have initially it's greater than r. Yeah, so initially we have just greater than r. So this difference right here is going to be Sn1 minus r, like that. Absolute value of it is like that. That's the difference. And then eventually we're going to get to a point here, because we can construct it any way we want, such that it's over here, and such that we're going to get it up to this point here. And also here I'm going to write this here. So we construct this such that this is going to be less than n1. Absolute value. Now here is going to go somewhere down over here, n2, and this is going to be again. This is going to be this is going to be absolute value of Sn2 minus r, and that's going to be less than absolute value of An2, like that. And then let's say we have another one here. So we have another one across here, 3, and then it goes somewhere here. Then we have one here, and get somewhere here. And so we can always construct it such that this is the case. And then let's go with a few. Actually, this one's at the bottom there. And then, this is Sn3. And then eventually we're going to get to, let's just call this n. And then eventually, so here. So as you can see, they get smaller and smaller because an is approaching 0. So because we could always construct that, we can always construct it such that it's less than 0. So then this part right here is absolute value Sn minus r, the oscillations. And this is going to be, and again, we can construct it less than an. And as you can see here, an is also approaching 0 then. So since an is approaching 0, all of these dots are going to be approaching closer and closer. So an is approaching 0 as n approaches infinity. An and thus Sn minus r as n approaches infinity. Let's put the bracket like that. Approaching 0 as well. As n approaches infinity, not 0. Like that. So yes, fascinating stuff. So yeah, this last example was a bit more abstract than my calculus book that had an absolutely horrible way of explaining this one here. But it's pretty straightforward. The answer is pretty much here in the hints. It gives it to you. And it's just dealing with the nature of infinite sums, where you could do pretty much anything you want with it, especially divergent sums. Divergent series, when we have positive and negative terms diverge, we could always get bigger and bigger numbers because there's no limit that it's approaching. Hence, we can do whatever it takes. It just takes more and more terms, so hence the difference of the oscillations gets closer and closer to 0. Anyways, that is all for today. Hopefully you enjoyed this another epic long video, and yeah, I'll be continuing this trend until I need be. Anyways, let's just scroll back up, and yeah, hopefully you enjoyed, and like always, you can download these exact notes. Yeah, this is a very long video. Exact notes in the link in the description below, as well as viewing these notes on Steemit, so you can download in PDF format or view it in article format on Steemit. That's yeah, pretty amazing stuff. And yeah, that's all for today. Thanks for watching, and stay tuned for another Math Easy solution.